Good morning. Welcome to the Mont-Blanc 2020 webinar. Actually, welcome to the HiPEAC conference because that's probably your first session at this conference. I'm Pascal. I'm the dissemination manager for Project Mont-Blanc, and I will be your host today throughout this tutorial. I will also keep an eye on questions when I'm not talking, so feel free to ask your questions to the speakers in the question tool. Don't use the chat for questions, please. So this is a full day tutorial, but we'll have regular breaks so you and us can get a coffee refill. And we will also have a long break for lunch so you can attend the HiPEAC keynote. So this tutorial will be a mix of talks and demos. Now, in this virtual format, it's difficult to have proper hands-on sessions, but we'll do our best to share a lot of practical information, tips and lessons learned to help you get started with the tools we're describing. So you'll see a lot of code today. This morning, we will first share with you our context, what our project is about, and then the simulation tools we selected and worked on. Then BSC will introduce you to the multi-scale simulation approach, and we will then take our first steps in Gem5. And in the afternoon, we will tackle SVE with an introduction and some programming tips, and we'll finish with a Gem5 SVE hands-on session. And we'll do our utmost to be finished by 5. Actually, I have to finish by 5 anyway, because I have to be home before the curfew. So let me introduce our wonderful team of speakers. Here they are in order of appearance, and most of them are online now. So Alejandro from Atos will present the Mont-Blanc simulation workshop framework, sorry. And then Adria and Francesc from the Barcelona Supercomputing Center will present the multi-scale simulation approach. Then Gregory from Atos and Joel from Cyprol will take you through your first steps with Gem5. And then this afternoon, we'll have our ARM team. Richard and Javier will moderate and present the sessions. We'll also have a pre-recorded talk from John Linford, Director of HPC Applications at ARM. And Bino from Jülich will share with you his programming tips for SVE. So a big thanks to all of them for being with us today. So now that you know the team, here is the tool we are going to use, and I'm not talking about Gem5. We know you've probably had a lot of Zoom meetings and webinars in the past months. So to turn this one into an interactive and we hope fun experience, we will use Mentimeter. With Mentimeter, we'll regularly launch polls, questions, and quizzes so that we know you better and to test your knowledge as well. So we hope you will all take part and enjoy it. Now, to connect to Mentimeter, it's very easy. Ideally, you need a smartphone, but you can connect from your PC if you don't have a smartphone or if you don't want to use it. There is no app to download. You just need an internet browser. So please connect now. We're going to make a test. Please connect to menti.com with your favorite browser on your smartphone if possible, and we're going to do a test. So once you connect to menti.com, they will ask for a code. So the code for this session, my session, is 2390370, and I will display my question. We would, as I said, we would like to know you better. So we would like to know where are you based? In which country? So what do we have? Belgium, Switzerland, Greece, Italy, France, Norway, Turkey. Anywhere else? Oh, our speakers are not participating because we have speakers. Well, we have me in France. I'm in France, but we have speakers in Spain, in the UK. Yeah, excellent. Excellent. Okay. More people? Okay. Good. Thank you. So now we have tested Menti. Um, I will briefly present the Mont-Blanc 2020 project so you know our context. So Mont-Blanc 2020 is a cooperative research project funded by the European Commission, and our motto is paving the way to a scalable, modular, and power-efficient European HPC processor. I'll explain a bit about this later. Um, who is in this project? Well, the Mont-Blanc consortium has changed over time, but the core and permanent partners are the Barcelona Supercomputing Center, ARM, and Atos. We were in it, the three of us, from the start. And in the current phase of Mont-Blanc 2020, we also have CEA, that's the French Atomic Agency, the Jülich Research Center, home to the Jülich Supercomputing Center, Calray, that's a French fabless semiconductor company, Semidynamics, that's a Spanish SME specializing in Microsoft architecture, and Cyprol, the company that will bring to life the European Processor Initiative project. So actually, Mont-Blanc is a series of projects which started back in 2011, 10 years ago, and we are now in its fourth phase, Mont-Blanc 2020. The initial vision was to gather academia, research centers, and industry in order to build a scalable, power-efficient HPC platform based on low-power mobile technology, so ARM chips, the same ones used for mobile devices, tablets, phones, etc. Now remember, 10 years ago, at the time we started, ARM server chips were not available, so this was really visionary. But of course, it's not as simple as just developing the hardware. I mean, the project also had to create from scratch an ARM ecosystem for HPC, I mean, an ARM software ecosystem for HPC. So Mont-Blanc 1 and 2 were a proof of concept. They explored HPC computing based on the mobile embedded technology, and they indeed demonstrated the viability of ARM-based HPC cluster because they created the world's first ARM-based HPC cluster. It was deployed in 2015, and it featured over 2,000 mobile CPUs, and it was installed at the Barcelona Supercomputing Center. So then with Mont-Blanc 3, we reached a new dimension because in the meantime, ARM server chips were available. So we were able to prepare an industrial solution and test market acceptance. And a server based on our prototype was indeed commercialized by Atos. So you could say that we did reach our initial objective, but we felt we needed to go further. So in the current phase called Mont-Blanc 2020 and started in 2017, well, it's a bit different from the previous phases because this time we aim to contribute to the development of the European processor for big data and HPC. So the project addresses essentially SoC, I mean software system on chip design, and aims to create IP for the European processor. Now, Mont-Blanc 2020 is going to end very soon in March, and it's probably the last of the series. But the outcomes of our work will live on through the EPI project, the European Processor Initiative, which will use our IP. So what's in the project? What's in Mont-Blanc? Well, the different phases of the project have had a number of things in common. Most important one to our eyes, in all phases of the project, we've had a prototype, ARM-based systems available to the Mont-Blanc partners and sometimes to end users as well to test software and scientific applications on ARM architectures. In the current phase, our prototype is a demonstrator running on an emulator platform, but the approach, the co-design approach remains the same. It's very important to converge our work into a prototype to test our technical choices. Then we have software resources, or maybe I should say software tools. Now, the availability of a matching software ecosystem was, of course, a prerequisite for market acceptance of ARM solutions. So it's always been one of the targets of the Mont-Blanc projects to work on that. Mont-Blanc partners have developed over the years or have contributed to software tools and resources that help programmers and architecture designers. So these include scientific libraries, a set of development tools for debugging, for performance analysis, for performance prediction, and also automated kernel optimizations. Then applications are an equally important part of the ecosystem. And over the years, we've analyzed series of exascale class scientific and engineering applications and tested them on the different platforms available during the projects. And we've done that too during Mont-Blanc 2020. For example, we've ported applications to SVE. And finally, a very specific objective of Mont-Blanc 2020 is to develop building blocks for the future European HPC processor. So as I said earlier, the objective of the team was to design and demonstrate ASIC modules so that this IP can then be productized within the European Processor Initiative. So Mont-Blanc 2020 is more upstream than the previous phases. We will not go up to the product stage, but it's all in the plan. Last thing I wanted to mention, I would like to introduce Debona because I know that some of our speakers today will mention it. So I wanted to show you Debona. Debona is the ARM-based prototype built by Atos during Mont-Blanc 3. And it's still in use, actually. It's been maintained as part of Mont-Blanc 2020, maintained in use. It's been used for various hackathons and trainings. It's named Debona after the Debona peak in the French Alps. You know, we've kept the mountain imagery. It started operation in the autumn of 2017, and it's based on Thunder X2 processors from Marvell, relying on the ARMv8 instruction set. And the prototype leverages the Bullsequana infrastructure from Atos. So it's, for example, it includes direct liquid cooling. It's cooled but with warm water. And with this prototype, we were able to show that our simulation environments were in accordance with real applications. So it's a vital part of the Mont-Blanc project, and it has become a main reference for our project. Now we'll stop talking. If you want to know more about the HiPEAC, starting again. If you want to know more about the Mont-Blanc project, we have a virtual booth here at the HiPEAC conference. So we hope you'll visit us. And we also have a website, a Twitter account, a LinkedIn page. So lots of means to get in touch with us. So very short quiz to make sure you're all still here and awake. So I must go to the next question. So what is Mont Blanc? Please select the right answer, and hint, there may be several right answers. So first one is Mont Blanc is a delicious dessert or a research project that contributes to the future European HPC processor or the highest mountain in Europe, or a research project that built the first ever ARM-based HPC cluster? Come on, I want your answers. There may be several right answers, you know. Okay, so that's good. You've really been listening to me, but actually all answers were correct. But if you remember number 2, a research project that contributes to the future European HPC processor, then we are very happy. That was the main lesson for my presentation. Well, now I'll hand over the mic to my technical colleagues. So, Alex, are you ready to take over?
Hello, Pascal. Yes. So I will share my presentation. I think you need to stop sharing.
I need to stop sharing?
Yeah.
Okay.
So, hello everyone. As Pascal said, my name is Alejandro Nocua. I work in Atos since 2019. I was part of Mont-Blanc 3 and now Mont-Blanc 2020 and the API project as well. Today we are going to, I'm just going to move this. Today I'm going to introduce the Mont-Blanc multi-scale simulation framework. I'm going to present the overall framework and how we are going to tackle it during the day. So high performance computing systems today consist of several hundreds of compute nodes. The complexity of this system is increasing as the number of computing nodes and type of interactions are increasing. These interactions we need to target to analyze as the hardware and the software and how they communicate with each other. With the changing hardware architectures also comes changing the software. So we need to know how our software will do with the new hardware where we are available. Or in case it is not available, to have a prediction of the performance of these workloads in order to understand better the system and fine tune it. In this case, modeling a simulation plays an important role as it can help us to predict and analyze and improve our systems. The Mont-Blanc simulation framework is a simulation methodology that aims to be efficient, accurate, and scalable, and also that will allow us to explore different possibilities of our architecture. Our vision is to have a multi-scale flow, a workflow that consists several tools that address different abstraction levels, and also that allows us having different information from lower level information like microarchitecture or instructions to computer or clusters. At the beginning of Mont-Blanc 3, we selected four main tools as the starting point. The first one, in this plot, we can see a representation of these tools. The higher that they are placed, the faster these tools are. And in the case of the scope on the x-axis, we can see which kind of information will provide us. Our idea was then to first target the Gem5 simulator that is widely known back in 2015. So it was missing a lot of functionality that we implemented through the project. Also, we can see TaskSim and DMMAS. There are two tools developed by the Barcelona Supercomputing Center and the STT macro. The STT macro is a simulator tool from the Sandia lab, and it was our starting point to analyze. So the main idea was to build on top of these existing tools. The first tool that I'm going to speak briefly, just as an introduction, is the MUSA tool. It is a combination between TaskSim and DMMAS, also developed by the Barcelona Supercomputing Center. The MUSA, the multi-scale simulation approach, has two main phases. The first one is a tracing infrastructure, thanks to the TaskSim capabilities, that captures the information of communication, computing, and runtime system events. Then these tools are then replayed in a high-level simulator in order to be able to understand how we can leverage these traces for simulation at multiple levels. Among the different analysis that we could perform with this with MUSA, then we had an experiment about simulating 265 nodes from 1 to 64 cores. Then the idea was to perform all of this information, all of this analysis, all of these experiments with different workloads, and then find which are the best for power consumption, the best for performance, or the best of both worlds. It allowed us to explore several architectural features, such as memory bandwidth, the number of cores, number of cache sizes, and vector sizes. For instance, one of the analyses that were performed was to test wider vector floating point units. and also scalability, quantifying scalability issues. Uh, with different analysis allow us to understand the applications and how the hardware reacted to these applications in order to see if it was an issue on the OpenMP and the parallelism phase, or it was a problem from the hardware side. We could get a first glimpse at the performance benefits and energy trade-off with increasing vector sizes, and we can also quantify the scaling issues in order to tackle the issues. MUSA tool will be further presented in the next presentation by our friends from Barcelona Supercomputing Center. The next tool that I would like to speak about is DMMAS Online. DMMAS Online is an extension of DMMAS tool from the Barcelona Supercomputing Center, and it was developed in in help with the collaboration of the University of Cantabria in Spain. The main idea was to transfer the concept from the STT macro, which uses skeleton applications. And skeleton applications is like we analyze an application, and then we identify the blocks of code which correspond to the computational phase. These computational parts of the code are then substituted by functions that represents the execution time of the application, reducing and the complexity of the simulation. DMMAS has for objective to predict the behavior of an application, and with DMMAS Online, the main idea was to further extrapolate this behavior. The overall workflow is once we have a skeleton application based on the ST macro tool, we then put it inside to DMMAS, and it will generate the statistics and traces, and then we will generate a parameter trace that will allow us to get insight of different portions of the code, how they're reacting, and how we can then further be improved. One of the main things that I forgot to mention was that the traces and are generated on a specific format, so we can visualize it in a great manner. DMMAS Online then can simulate tens of thousands of MPI processes in a faster pace than other tools. For instance, one of the analyses that we performed during Mont-Blanc 3 was to simulate Lulesh with 10,503 elements. And in this plot, we can see in overall, just to give you a representation of the kind of idea, was we target, can we simulate up to 16,000 number of processes, and which will be the restrictions. From one side, we can see that the STT macro will presented issues with the memory, up to 4,000 cores. However, with the Lulesh DMMAS Online, we can see that we could extrapolate this analysis up to 16,000 cores, 15,000 to be more precise. Also, what we did is that we performed a different analysis to see if our analysis was similar to that one that has provided by STT macro. And we see that they match it in a perfect way. The next tool that we're going to speak about, then we're going to go to a more detailed, slower simulation, is the Gem5 simulator. Gem5 simulator is a modular platform for computing system architecture research and encompasses system level architecture as well as processor microarchitecture. In this way, first we analyze how this simulator can help us to our goal of analyzing different workloads. Gem5 simulator is quite flexible, has different trade-off of accuracy versus speed. It can run the different instruction set architectures, different interconnect, and also different memory systems. This is quite flexible and allow us to change parameters in a different way so we can see how our workload is impacted. The main thing that we did then was how we can reduce the simulation time of Gem5. Gem5, as it is quite detailed, it will be quite a slow simulation. So one of the things that we did was to create a tool that we called Elastic SimMate, that is a trace-based driven simulator. The main idea of Elastic Simulate was to generate traces from an execution on the full system Gem5 simulator, and then these traces were replayed for different configurations. As you can see in the graphic, based on the traces, we can then change the memory hierarchy, analyze the cache of the size of the caches, and etc. This is one of the modes that we did for Elastic Simulate. We also went further and analyzed different tools with propose and with different modes. For example, the synchro mode allow us to perform weak scaling analysis, and the task mode based on OMS presented a strong scaling analysis. The strong scaling analysis then allow us to see how the application was scaling once we increase the number of cores. We can also then, with the same set of traces, change the configuration of the cache of the memory hierarchy, and then extrapolate the results. So it means that with only one run of collecting the traces, we can explore different applications and different um, set of memory hierarchies to analyze how it impacts the overall workload. Another tool that then we follow up is that we went to this Gem5 to increase the abstraction level. In this Gem5, it extends the simulation scope of Gem5 as we can simulate bigger clusters. It simulates multiple compute nodes running in parallel that are then connected into an extra simulation of Gem5. One of the main advantages is that we could simulate nodes of compute systems without having uh, to slow down the simulation pace too much. So it is roughly the same time that a vanilla Gem5 run. In this case, we then could validate this Gem5 against physical computers like Dibona, as Pascal mentioned, evaluate the sensitivity of different applications on the synchronization phase, and also perform scalability analysis, as we want to extrapolate these results on how it will impact the applications. Another tool or another thing that we focused for the Gem5 implementation was to add the SVE instructions. The Mont-Blanc project has been instrumental in the implementation of scalable vector extensions in Gem5. The work for the Gem5 SVE code started during Mont-Blanc 3 and has continued under the successful project Mont-Blanc 2020. In Mont-Blanc 2020, then we use it heavily for helping to port applications, deriving the right sizes for SVE implementations, generate traces for the applications, and also to focus on the activity factors that obtain the simulation that are used for reliability modeling and how we can then extrapolate this analysis and all the architectural decisions for testing our proposed NOC in the Mont-Blanc 2020 project. It also enables key applications to exploit them, as we can then analyze now, even if we don't have available hardware that already introduce the scalable vector extensions. So in overall, this is the Mont-Blanc simulation framework. The main idea then is that we have several levels of abstraction in which we can analyze one system architecture and then select which is the level of accuracy that we would like to know, or if we want to target on a specific part of the system with more fine-grained information. On today's talk, then, we are going to focus on MUSA, task sim, and DMMAS interaction, and also into Gem5, and we will provide a hands-on and first introduction to Gem5 for those who don't know Gem5 yet. And also in the afternoon, we will have a heavy and rich experience with a scalable vector extension. So in summary, uh, the Mont-Blanc simulation framework is a scalable and flexible workflow that addresses efficient design exploration for complex heterogeneous systems. It allowed us to get information for a wide range of implementation details, from microarchitecture to clusters. It also allows us to gain information about applications and how they behave in a given hardware for the future HPC systems. And thanks to the Mont-Blanc project also and all the research has been done, we will get insight and provide all of this insightful information into the next phases of the project, such as the European project initiative. So, as with Pascal, we will have a fast quiz that is can be reached on the Menti using the following code or scanning the QR code.
So, we're actually running ahead of schedule. I can't believe this.
Yes.
So, your quiz is not open yet.
Yeah. Let me see. It should be
Oh
open
yeah,
by
now
now.
it's okay.
So a first one is, what do you think about the Mont-Blanc simulation framework? We can use the heart button, thumbs up and thumbs down.
So can you show the results?
Yes.
No?
Yes, yes, yes. Um, you can see them?
Yeah.
Perfect. We have 10 thumbs up. Thank you so much. So in our rank the following tools from faster to slower. Which one do you think is the fastest tool that we presented in the Mont-Blanc project?
So we have Gem5, Dimemas Online, Elastic Simate, or MUSA.
Well, I think all of us voted. And the faster actually is MUSA. And the second one is Dimemas Online. So it was a close
You're
call.
not showing the results,
Really?
Alex. No.
Uh,
Are you showing the Menti?
yes, I should be.
That's better.
Ah, perfect. So after our last competitor, yeah, yes, it's exactly how this multi-scale simulation flow is working. MUSA is the fastest and Gem5 is the slowest. MUSA is also quite useful for get design space exploration and get several information, while Gem5 is quite slow but provide us a lot of fine-grained information. So the next one will be, let's see. In Mont-Blanc project was instrumental in the implementation of Engine 5. What do you think? It could be implementation of programming languages in Gen 5, or the scalable vector extension in Gen 5, or trace-driven simulators in Gen 5. I'm perfect. Everyone got it right.
Wow. Impressive. Even I got it right.
So you were listening. That's perfect.
Yeah. Or let's say I've been involved in Mont Blanc so long that
True.
I know the answers. Thank you, everybody, for participating.
So the next one will be, which tool allows the system simulation of a complete HPC system? Can be MUSA, Gem5, or Elastic SimMate. Yes, exactly. MUSA it is. Elastic SimMate even thought that reduces the simulation time. It is not possible to simulate a complete HPC system that as it will, based on the number of the system, of the core person in the system, the simulation will slow down as part of the Gem5 tool. The next one will be, and then finally, which tool is a trace-driven simulator on the following ones? DMMAS Online, Elastic SimMate, or Gem5? And exactly, Elastic SimMate is one of our trace-driven simulators. The other one is MUSA, and we will continue with MUSA so you can know more about it. So the final thing that I would like to say is that the slides will be available on our website, and I have added all of the links for all of the tools that we spoke during this presentation, as well as the link to the one of our deliverers about the simulation framework that has all of the presented examples, as well as the analysis that we could accomplish. You can go to our website, it's directly available and open access. Thank you so much to everyone.
Thank you, Alex. So yes, that's an important point. The presentations will be available on the Mont-Blanc website, and I will send the link to all attendees because I have your email addresses. So to all attendees and registered attendees. So we are ahead of schedule. Should we have the break now, or do we, Adria and Francesc, do you want to do your presentation after the break or do it now?
I think we had the break anyway before our talk, right?
Okay. So
it was scheduled anyway. If you have the
yes,
agenda.
I will share the schedule if you wish.
Perfect. Thank you, Pascal.
Okay, so this is our schedule. So we are ahead of schedule, but we'll have the break anyway, because there might be people who want to join us for the next presentation. And if we start early, then it will miss the presentation. So we'll have a break now, get another coffee. I will get another tea, and we start again at 10:40.
If you want, we can go earlier. I mean, as you wish, Pascal. But we did have a break. That's why I mentioned the break.
Okay. Do you want to start at 10:30? It's just that I'm afraid some people may miss the.
Okay, let's follow the
beginning
agenda.
of the
It makes
presentation. Let's
sense.
keep to the schedule. Okay. Or do you need more time?
No, I think it's fine. Let's follow the
Okay.
schedule. I mean, it's fair for people that wants to join late.
Yeah. Okay. So we'll see you at 10:40 after another tea for me. Thank you. Okay. So, Francesc, whenever you want.
Okay. My name is Francesc Martinez. I work at the Barcelona Supercomputing Center as a simulation engineer, and I've been
A bit
working.
louder, please.
Sorry. My name is Francesc Martinez. I work at the Barcelona Supercomputing Center, and I've been working as a research engineer from the Mont-Blanc 2 project, Mont-Blanc 3, and now Mont-Blanc 2020.
The sound is very bad, Francesc. Sorry about this. So, yeah? We can't hear you. So?
We cannot hear you now, Francesc. Maybe you need to change inputs.
I promise it was working when we did the sound check this morning before starting. Sorry about this.
He'll probably be back in a sec.
Okay. Do you hear me now?
Yes,
Yes.
that's much better.
Sorry for that.
However, we can't see your screen.
No, yeah, I have to share. Okay, now. Okay, now better. As I was trying to say before, my name is Francis Martinez, and I work at the Barcelona Supercomputing Center. And I've been working as a simulation engineer from the Mont-Blanc project, Mont-Blanc 3, and now Mont-Blanc 2020. And I will introduce you MUSA, our multi-scale simulation approach. The outline of the presentation will be just first a brief introduction to the MUSA framework, and then 3 short videos that outline the 3 sessions that we normally do of our tutorial. That normally would be 1 hour and a half each, but we will just show you the results and not wait for the execution time, and it will be much faster. Okay, MUSA, it's used to trace and simulate hybrid applications, and by hybrid I mean applications that use both MPI and OpenMP or MPSS. And we do that by tracing different, by first analyzing in different steps, first the MPI events. Here we can mark in red, and the simulation phases that don't contain MPI that are here marked in gray. And if we would zoom in, we would see that the steps without MPI usually have the OpenMP parallelism, parallel force, OpenMP tasks, etc. And what we want to use MUSA for is to study how these applications behave, not in current day systems that we could run them natively, but in future systems or in systems that have not been built, with different number of cores, cache size, associativity, different network topology, different DRAM technology, etc. The main motivation to have one of the key steps of MUSA is that if we have a very simple simulator that only uses for every MPI and OpenMP event, the native duration, we would see that the performance, if we plotted the performance that the native application has and the performance that we would simulate, we would have a very big error. That's due that with just taking into account the event durations, we cannot simulate a lot of things, including resource sharing and contention of resources. Also, one of the points of MUSA that we want to tackle is that architectural simulators that could simulate that in detail proper are very slow. If we want to simulate 10 seconds of a native execution with 16,000 cores, assuming a standard frequency of CPU, we get that it would take 10 CPU years to simulate that application properly. And we need some kind of approach to be able to have a similar accuracy, but do not spend 10 years waiting for the results. Our solution is MUSA. That's the multi-level simulation approach. And what this multi-level simulation means is that we will separate the complexity of the application in different layers. First would be the network simulator that will simulate only the MPI events and MPI related message sending, etc. From the computational burst between MPI events that will be done simulated with an architecture simulator. Separating this allows us to first have different levels of complexity on the simulation, on the simulating part, and later being able to parallelize the architectural, the node, the computational outside of MPI simulation. What we do is like the third bullet point says that, and it's a limitation of our approach, that we have to generate the trace, and this trace hard codes the number of MPI ranks that we are tracing. We cannot change that dynamically in the simulator because all the information, all the message sending of in MPI, it's computed at tracing time and cannot be changed. But the nice thing is that the things inside the architectural simulator, the number of cores per MPI per rank available on OpenMP or MPSS, we will be able to change them at simulation time. The first step that we do is generating the trace. We have the compiled binary of any application, HPCG, rules, etc. Any application that we want to trace and simulate. And there will be 3 steps. There will be the first one, the more exterior one again. It's with an MPI call instrumentation library. It's an interposition library that has very little overhead. We trace the behavior of the MPI library. We trace all the primitives. Then we do another simulation without tracing those primitives, but this time we have we run against an OpenMP runtime that allows us an instrumentation plugin that again has very little overhead, and we can trace all the parallel for, all the OpenMP tasks, and all the other OMP events, task weights, etc. And we can record them and their duration and the duration of the computation phases between OpenMP events. So the duration of the OpenMP tasks. And then in the third step, that adds more complexity, we run the same binary through Dynamo RIO. This allows us to trace for every computational phase between MPI events and for every OpenMP task and for every computation and for every part of that task, what instructions are executed and all the memory accesses that they perform. And finally, we can merge all this information on the 3 steps in one single trace. Good. Then the second step is the simulation. We have the trace with all the information that I just told you, and we use first, well, in truth is at the end, a network simulator to simulate only the MPI bits, communication and so on. And for every computational phase between MPI events, we use a multi-core simulator. This multi-core simulator that Alejandro told you, it's TASIM, and it's compiled against the same OpenMP runtime that we have generated the trace with. So we know that the behavior of the simulator will be the same behavior as the native execution. And this allows us, this feature allows us to run any number of cores that we want. In this case, in this figure, it will be 2, but we could have run any number of them. And here we go back again to the motivation that we have, that if we just use the strict duration of the phases, we get a huge error. But if we add below an architectural simulator that can simulate resource contention and sharing and cache sizes, we get a much better result. And this is accomplished still not taking 10 years to run every single simulation of a 10-second small burst of a benchmark. Okay, this is more a formal introduction, as I told you before. MPI plus OpenMP or MPSS. MUSA is the network simulator that handles MPI, and TASIM is the architectural simulator that handles OpenMP or MPSS. As I told you, trace-based. We generate one time per number of MPI ranks. We can change at simulation time anything about the architecture. The number of cores per MPI rank, cache sizes, associativity, DRAM technology, if a cache level is shared or private, etc. Yes, as I told you before, we have 3 levels of cache. Okay, this is again the same thing I have told you. Sorry for that. Yes, a little bit more information about the OpenMP part. For this approach, we cannot run standard compiled OpenMP with G++ or Clang++. We have to use Mercurium, that's a source-to-source compiler developed at BSc, because it links against an OpenMP or MPSS runtime that it's Nanos, that's also developed at BSc, but publicly available. And we have developed the instrumentation plugin for Nanos. And also a little information, when we generate the trace, we generate it only with 1 core per MPI rank, not with a lot of them, because it's easier to just store the information properly then. Yes, and as I have told you before, to trace the instructions and the memory access, we use DynamoRIO. That we have just coded a plugin for it, and we run it. We can run it alongside other plugins, and this allows us, for example, to run it against the Army plugin and be able to run and trace SVE applications in a machine that does not support SVE, because Army provides us that feature, because they also Army is coded as a DynamoRIO plugin. And yes, I jumped the shark a little bit. This is what I just told you. And now we are able to trace SVE through Army, but we want to develop through DynamoRIO native SVE support in machines that support it. Okay, so as a bit of a summary, all the information is stored independently. Every MPI rank has its own file. Every segment of every computational phase between MPI events is stored independently. Every OpenMP task between the section is also stored independently, and the memory accesses and instructions of every segment independent. Yes. And this will be a bit more in depth, what I just, this trace generation step that I have told you before. The extra implements the MPI interpretation library, the DynamoRIO, the instructions and memory access, and the Nanos plugin OpenMP stuff. And everything generated here, all the information generated here, we consider the MUSA trace. Okay. Usually we do this as a tutorial and allow access to a machine. So we have the requirements of GCC 7.1 or higher, OpenMP 3.x or higher, Python, lmod to load modules, and army if we want to for SVE tracing. And we recommend using Slurm to manage the queuing system of the HPC cluster. Otherwise, it can be a headache. And this is all the applications that we usually attach in the package. Our architectural simulator sim, network simulator DMMAS, X-Drive, that's a performance analysis tool, Paraver, that's also not performance analysis tool, but it's a visual performance analysis tool that you can use to visualize the data. I will show you later. OpenMP or MPSS runtime, compiler, the scheduler, the Namorio, and the things that I may not have said, Ramulator to simulate DRAM technologies. We can also support DRAM Sim3 and ARMY for the SVE support. Okay. This is the tutorial that I will show you. I have done it in the Mont-Blanc 3 prototype, Divona, as Kale has said before, introduced. Due to the limited amount of cores for a normal tutorial, normally if we have 20 users, we have to limit a lot the size of the tutorial. The results may not be extremely representative of the application, but it should be enough to convey how we use the our simulators. Does anybody have any question at this point?
I don't see any questions.
Oh, okay. Okay, if they ask anything, you can interrupt me at any point.
I will.
Okay. Okay, then the first step would be the first tutorial. That will be, normally it's also, yes, a 90-minute session, but the video will, we recorded a video not to run over the time. That can happen very easily. And it will show you the steps that we use for the first simple simulation approach. It will have the environment setup, generating the trace.
Sorry, we have a question, Francesc. Can I interrupt you? It's in the chat. It's not in the Q&A.
Yes.
With MUSA, you are not actually executing code, but only reusing execution traces. Gem5 is not used to run the code. Is that correct?
Yes, that's correct. We execute it one time to trace it, and then we get the trace, and we never use the application binary again. We don't simulate the binary itself.
Thank you.
You're welcome. We are just purely a trace-based simulator, both TASIM and DMMAS and the whole MUSA approach. Okay, as I was saying in the first session, we'll show you the environment setup of MUSA, how we used to generate a simplified trace without the insertion execution data. That would be the 91% error approach, but it's needed for later. We will simulate that trace and we will look a little bit at the result. Let me load the video. Welcome. This is the video for the first session of the MUSA tutorial. In this tutorial, we will show you how we use MUSA to trace and simulate an application that uses MPI plus OpenMP or MPSS. We distribute MUSA usually with a module file for the clusters that we install it on. To start the tutorial proper, we should go to an empty folder. For example, let me show you. Okay. And the command that we have to start is MUSA start. This command, what it does is it copies a set of files, the tutorial instructions folder, the binaries that we'll use in this tutorial, in this case HPCG. We will use HPCG with 4 MPA ranks and a very small input size. And we have 2 binaries because one of them is the unmodified binary of HPCG, and the other one we have modified it by linking against the instrumentation library of our OpenMP and OMPSS runtime. Besides the binary, we have 3 bash scripts, one to generate the native runs, one to generate the simplified mode trace and one to generate a more in detail trace. All scripts are simply Slurm scripts. To submit it to the Slurm queuing, you just use batch, and the native executions will be run. This is useful to have a first benchmark to compare against, and we can generate the speedup graph of this native execution with another script that we have copied, and this script, when the native execution finishes, will generate this speedup graph. In this case, for the tutorial that we do, the speedup graph has a very bad appearance, but this is due that because the input size is very small, and we are oversubscribing the ranks. Okay, now the second step would be to generate the trace proper. In this case, let me show you the script that does it. It's another time very simple Slurm script, Slurm header. We load the module for the same binary, input set, number of MPA ranks, which matches from the configuration option and the Slurm header. And then the only other relevant parameters are memory mode is disabled for now, it will be enabled in the second session. And this is a list of the number of cores per MPA rank that we want to simulate later on. To generate the trace, it will be again just submit it to the Slurm system. This trace generation has very little overhead and would take 2-3 minutes. Usually it takes around 2 or 3 times the time that it takes for the native application to execute. But let's not wait, let's go to a folder that already has the results. If we go to the step 2 folder, we can see that here, aside from several log files, we have an output trace. And let me show you the trace the folder that contains the trace. It has the trace proper with information that our simulators can run, the logs, and a folder to continue with the simulation. Let's first look at the log folder, and this will allow me to explain you that there is several stages in generating the trace. The first stage, it traces all the OpenMP and OpenPSS events in the simulation. The second step traces all the MPI events, and then later on we have to modify the traces generated in the first 2 steps to mix the information and to convert them to a format that our simulators can read. Now let's look at the trace itself. If we go to the trace folder, there is the folders, one with the TASIM trace, that is the single node simulator, and one with the Paraver trace. That's the one I will show you now. This is the trace used for the network simulator, and also it allows us to observe the general behavior of the application. If we open this trace with Paraver, that would normally be wx paraver and the name of the trace.prv. If we had the graphical interface, we could do it here. I have done it in my laptop. We can see the behavior of the application. In this, I have opened 2 windows. The top window has, well, all of them have 1 MPA rank per line, and left to right is time. They are color coded. In this top case, it's just state. And here we see the blue is running, orange is waiting communication, and we have yellow lines for communication between two different ranks. In the bottom one, instead of just state, we can see exactly at which MPI event we are looking. They are color coded, and we have here at the bottom what they are. Black is a set of MPA, so used for computation. Blue is MPA send, etc., etc. If we wanted to see what is the behavior of the application, we can zoom in, and we can see that it has several iterations. More or less, they appear to be regular. the bottom rank is always weighting more than the rest, and if we wanted to look more in depth, we could see that the faces seem to have 4 different and distinct behaviors, and in the last there is a lot more communication, and we could zoom in and see the different communication arrows that now they become clear what they are. Communication from rank 4 to rank 1, 2, and 3, and so on. And if we wanted, we could go even more in depth here in the last one, and we could see exactly what MPI events are happening inside. Because from the outside it looked like a single unified event, but if we look inside, we see that there is a lot more happening. This trace in the beginning doesn't have that much useful information for us other than being able to observe closely the binary application behavior. Okay, now that we have seen the trace that we have when we have generated it, let's go to simulate it. There is 2 folders, one for the pre-simulation and one to integrate the results. They allow me to show you with the windows that I have shown you before. If we go outside again, what we do in this, to simulate it faster is we divide all the time of the application as computation phases between 2 MPI events. All the time that we are outside of MPI, and we separate it so that we can simulate it independently. All these computational phases between 2 MPI events we call MPI phases. Okay, now to simulate all those MPI phases, we first off go to the, in this case it's already been simulated, but allow me to show you what we would usually do. We have a script that generates the simulation. What this script does, it generates one simulation command per MPA phase, per MPA rank. And this file with all the commands is this one, the all commands. And we can see that there is a lot of repeating commands with the same structure. We just change folder here and invoke this node simulator with the configuration file, the input trace, and the MPA phase that we want to simulate. This is very simple, but as you can see here, there is 17,000 commands for a very, very simple application. And in this case, also there are this many commands because we have 7 different number of cores per MPA rank configurations, and we will simulate them all. And to simulate all these commands that are in a bash-like file, we use Greasy, which is a simple parallelizer that will allow us to run one command per core in a single node. And to run the simulation propers, there is another script that's also very simple. It's an Slurm script with a header, and we just load the MUSA module, and we just run Greasy and the name of the file with the commands that I have just shown you. And these commands will be run one at each core. Whenever one core finishes, it will be replaced by another one, and we will have a simulation log here that I can show you. We can see that all the simulations finished okay, none failed, and all the simulations for a very simplified mode took 2 hours with 48 cores. At this point, what we already have is every MPA phase simulated independently, and from this moment, if we look at the parameter trace and we get the information about the periodicity of the phases, we could extract some results. But for the tutorial, we consider that it's better to just integrate all these results in a general trace with the network simulator, so we can have a single result, so it will be easier to show the results themselves. In the simplified mode, we don't need to do anything here. We just go to the integration folder, and there is an integrate script that for every configuration of course per MPA rank does the integration. It's a very fast script. The network simulator is very fast, and the simulator, what we will do is generate a parameter trace of the unified simulation. Again, I can open the parameter trace here. This is the simulated trace with 4 cores per MPA rank versus the original trace of the original execution. And these now have the same time scale, and we can see that we are faster. There is some improvement, and if we look at the overall behavior, we can see that the initial phases here in the second iteration are very different. So if we go in depth here all of them are compressed. In the simulation, we can see that these phases have sped up significantly, while these others have not. Now let me to verify. Now both have the same time scale, and we can see that these phases have compressed a lot, and some other phases are still taking the same amount of time. This allows us to verify that there is some phases that have been sped up and some that not. In this case, we would have to take a look at why some of them have not, if they are purely sequential or if the parallelization is not working properly. Generating these traces also allows us to have, again, the speedup graph. If we go back to the root folder and execute the generated speedup graph, we can not only see, like before, the native execution speedup graph, but also the speedup graph of the burst mode simulation. That's the simplified mode simulation that we have just done. And as we can see in this case, because in the simulator we will not be able to simulate the oversubscription events and the fighting for resources, the simulation time of our burst mode simulation is much faster. We are not trying to simulate oversubscription in this case. Okay, and this will be all for the first session of the tutorial. Okay, that was the video for the first session. Does anybody have any questions or anything that they want to ask? Because it may have been a little bit fast.
I don't. Sorry, I don't see any question for the moment.
Okay. Just to elaborate a little bit, the things we saw in the simulator at the moment, in this step, it's all the information that we have, because only have the duration of the simulation, the high level simulation. But later we could have a lot more data in that trade. I will show you later and tell you examples about. This is the speedup graph that we had, and again to reiterate that it's now the speed of the native application is so bad because we are running the 4 MPA ranks oversubscribed in a single node, and the bar simulation cannot detect that, and we cannot really detect at the moment MPA rank oversubscription. We can detect.
We have a question.
Yes.
Okay, so it's a question from Guy Paolo or Paolo Guy. I don't know. I just see your nickname. What was the difference between the 2 final schedule version? Was it a different schedule of the task or of the precedence relationships? Because the number of TEH cores was the same.
No, in the trace that I showed in the video, the difference is that the second trace that I showed, it was not the trace of the top one. We had 2 traces. The top one was the original execution, and the bottom one was the simulated trace. And in the simulated trace, instead of running with 1 core per MPA rank, we ran it with 4 cores per MPA rank. That's why some regions were really sped up. Because let me change the video again. If we go here, let me both have a little bit here. let's say, all these simulation, both views have the same time scale. So if this took this time, this iteration, this here took way less time. And that's because the simulation of these parts was sped up. The other parts here seem to have more or less the same duration here, down here. That's the difference between the two views. I hope that answered the question. And so again, the scheduler that we use in the native execution here, it's the same that we use for the simulations down here.
Thank you.
You're welcome. Okay, if there is no other question, I would go to the next session that we do a little bit more in detail simulation. Right, I should have changed before. Okay, in the second session, what I will explain you is the first simulation was the very inaccurate one because we don't simulate any of the resources. And in this one, what we do is we add tracing with an RIO to some specific regions. We extract the instruction executed and the memory addresses accessed, and we run all those memory access to the node simulator, and that gives us, when we augment the number of cores per rank, a more detailed simulation of the resource sharing contention. But the outline of the video will be the same. We will generate the test at the beginning, we will execute the simulation, and then we will see the resulting traces. Welcome, this is the video for the second session of the MUSA tutorial. In this video we will show you how we trace and simulate the same binary applications that we used before, but in a more detailed mode. To show you that, we are still on the same folder as before. We can go to the bash script that will generate the trace to show you the other parameters that we ignored before. In this case, we have activated the memory mode tracing to have a more detailed information, and there is some other options that allow us to filter from where that detailed information comes. In this case, we will only trace the first MPA rank, we will not trace all four, and we will trace from the MPI phase number 352, and we will only trace 20 phases in detail mode. We do this because the detail mode trace contains a lot of information, and running everything in detail mode would be very expensive, and we feel that taking just a little bit of information in a more detailed mode and being able to understand a small part of the code very well allows us to extrapolate the information that we know to the rest of the iteration of the code that usually behave in a very regular way. The other configurations options are the same as before, the number of cores per MPA rank, and the headers and everything. To submit this script to generate the detail mode trace, we just need to send the script to queues. In this case, we will not do it because this tracing takes a significant amount of time. I will show you now which step we have added and why it has a significant amount of time. If we go to another folder with the results here, we can see here we have trace in detail mode. I can go to the trace folder, to the log folder, and show you. Here we have the same log files as before, but we have here a new log file. The memory tracing is the second step that we do. In this step, we execute the normal binary, but we execute it through DynamoRio. DynamoRio, it's a dynamic library to instrument the code. It allows us to trace exactly what's happening in the simulation. We will know which instructions have been executed and the addresses of their memory accesses. When we trace this, we also trace all the OpenMP or OMPSS function calls to know all the events, so we can assign the instructions and the memory accesses to the proper OpenMP task that they represent. So we can later simulate all the OpenMP tasks with the proper instructions that they need to simulate. Now let me show you a bit the log of out. I don't remember. In this case, here we can see the invocation to DynamoRio. In this case, you can see that, and that's one of the nice reasons that we use DynamoRio, is that, for example, the army, it's built on top of DynamoRio as a DynamoRio plugin, and if we want, and we have done it, and we do it sometimes, we can run SVE applications through the DynamoRio Army plugin with our tracing plugin on the side, and we can obtain execution traces of SVE binaries with the same logic. In this case, this information is outputted here in a temporary trace here. And then in the third step that we also had, we merged that information with the information we already had. That would be all the information that we need to know about the trace generation in detail. And now we can go to the simulation step that has some other differences from before. Okay. Now we have the same thing as before for the moment. We have the script to generate the pre-simulations, and in this case the file with the simulation commands, in this case, has a different number of commands to run. Some of the simulations we have already done, simulated everything here. So now we have more configuration files because we have to simulate memory mode simulations. Because we chose only to have 20 MPA phases, the information in detail, we will only run 20 simulations in detail, multiplied by the number of configurations. If we look at the log file, we can see that even this, even after reducing the number of cores per MPA rank and not running all of them, just running the tail mode simulations, some of them take very long, very long, and that's why we don't run all of them in detail mode, or not even a large number of them in detail mode, because they would take a significant time. This in the simulator is done via a new script that we did not show in the first session, that is the extrapolate burst duration, and this calls well, it's it's a Slurm script. This one is also very fast because it doesn't have to treat that much data, and we just load the Python script and MUSA, and we calculate the correction with the one core simulation and the contention with the multiple core simulation. And with this, we obtain a different set of results, that is the integrated results. And once we have the results, we, exactly like before, we can go to the integration folder, and we have the integration script that we can run, and we get the simulated traces that will have a different behavior as before, and we can look for it. This is the traces that we have generated in detail mode that contain all the data, and we can see this is comparing two different simulations. The top has 2 cores per MPA rank, the bottom has 8 cores per MPA rank. And if we zoom in, we can zoom in here. Okay, now we can see both graphics are from different traces, but they have the same time scale. And we can see that in this case, this initialization of the benchmark goes much faster, and some of the computational phases are not sped up that much, but some of them are. In this case here, this one here it's significantly sped up, but some of them, like the first big iterations, are not sped up that much. And this allows us to verify how the resource contention or the memory patterns affect the different core configurations per rank. And we could compare how, in this case, the memory mode affects the simulation of the trace. And as we did before in the first session, we can go back to the root folder and we can generate the speedup graph. I don't have the graphic interface, but I can show you the result graph. And in this case, because the benchmark is a complete toy benchmark, a very small input, and we didn't trace that many memory mode phases, the results we obtain have the exact same scalability. Regretfully, it would have been nice to see a difference of behavior to be able to explain some things, but because of the time constraints, that's all we can show right now for the tutorials. Okay, that's the video for the second session. A couple more things that I forgot to add in the video or removed during the editing. The reason we also don't trace more than 20 phases for the tutorial and more for the real case is that tracing through DynamoRio adds a very significant overhead, and tracing only a portion of the benchmark allows us to do the tracing in a reasonable amount of time, maybe 30 minutes instead of having to wait 8 hours or 10 hours. And DynamoRio allows us to, let's say, run the parts of the code that we don't want to instrument with very little overhead, run the parts that we want to instrument with the overhead that we have to pay. We cannot run it any faster. But when we finish, we can dump the instrumentation and continue to execute fast again. And the second other thing that I forgot to add in the video, you may see that the results in the parameter view that we are observing don't match perfectly the speedup graph, that the data seems a little bit funny. The speedup graph only takes into account the region of interest of the application, and the parameter trace is the full application, including initialization and resource freeing in the end. So that's why the speedup graph here might not have the same percentage as the parameter trace view. Okay, and I think this is all for the second session. Is there any question?
No, no question.
Okay, I hope it is because there are not because people don't understand what I'm saying. Okay, and let's see the time. We are good on time, I think. We can go to the last session.
You have 12 minutes left.
Oh, okay, yes. It's 6 minutes video, the last one only. The third session, okay, the conclusions for the second session is that we can simulate with different architectural parameters. In this case, we have not changed them, but we can change L1 cache size, associativity, number of MSHR registers, levels of cache, the DRAM technology, everything. But also we have to remind that this is a first approach because we parallelize the simulations, we have cold caches, and there are some errors that we know what we have, and we have to take into account when analyzing the application that maybe there is some applications that due to the cold caches would behave extremely differently or not that differently, and we have to look at them. Also, when I chose the 20 phases, which phase to start, and then the extrapolation that I glossed over because it's very complex and I cannot explain properly in the tutorial, we have to try to simulate in detail one full iteration of the kernel that we're simulating, and when extrapolating, we have to be able to tell them how many phases does a single iteration take, how many iterations there are, to be able to extrapolate the information that we get from the detailed mode to all the trays. If we don't take care when using those parameters, the results that we get may not be good. Also, we know that for some of the parameter configuration, like the vector register size, we are very optimistic. For the vector register size, for instance, we assume that the compiler would be able to fuse all loops that affect vector registers into using bigger vector registers, which most of the time it's accurate, but in some cases when the loops are long, it may be overly optimistic. Okay, and we read the questions. What to do the conclusions. And now the third slide, the third session, sorry. It's the most interesting part. It will be the design space exploration. That's the main reason why we use MUSA. And the benchmark, the design space exploration example that I will show you uses the same benchmark. That's very memory dependent, but actually we have a very small input. And we have 3 different architectures selected. One that mimics scale-like architecture, that we use in milestone 4, our supercomputer in BSc. One that's a high-performance ARM system, standard X2 with HBM memory, and one that would simulate a low-power ARM. So that's usually simpler, but much more memory efficient. And that these are the differences that we have chosen to put into the system: the frequency of the simulated system, the number of instructions committed per cycle. We put a higher one for the ARM high performance, an average one for the -2, and a lower for the low power ARM. And then same L1 cache, little bit different L2 cache and L3 cache, different DRAM technologies with different speed. Now let me show you the video. Welcome, this is the video for the third session of the MUSA tutorial. In this session we'll show you how we use MUSA to generate a very small design space exploration test. We are on a separate folder that everything has been finished. We are in this folder that contains the same memory test that we generated in the second session, but before running the simulations, what we will do is look at different configuration files that we use. This would be the 3 different configuration files of the architectures that we will run. The different architectures would be ARM high-end, ARM low power, and one that replicates Mare Nostrum. That's our supercomputer. If we look at the files, few of the changes are the CPU frequency of the CPU that we are simulating, vector register length, output buffer size, reorder buffer size, issue and commit rate. Caches are the same and at the first level, but change at the second and third level. And these 3 files try to express 3 different architectures that we could want to simulate. To generate the steps generated in the previous sessions, we will just need to have a bash script file that generates the same for the same binaries and has a list of the configuration files that we want to simulate. In this case, we are 3. When we do design space expression, it can be thousands. We will just create the simulation environment that I have already done, and if we go to the simulation folder, what we would have is for every configuration file that we saw, and for every number of cores per MPA rank, 2 configuration files, one for simplified mode, one for detailed mode. To generate all the simulation commands would be like in the previous sessions. Generate all the MUSA commands, and to launch them to simulate, the same, launch all MUSA frames. In this case, let me show you that the number of simulations has gone up significantly. Now we are already on 44,000. And in this case, that this would take between 6 and 7 hours. After doing this, we would normally analyze the results, but to show you the final results, we have already executed the extrapolation scripts and we have already integrated the traces, and I have opened the results here in Paraver. What I have just loaded first on this, the leftmost set of 3 images are the total duration of the simulation. On top is ARM low power, ARM high end, and the Mare Nostrum equivalent. We can see that they all have the same time scale, and we can see that the performance of the ARM low end that we have configured with smaller caches and smaller CPU is significantly slower. And between the ARM high power and Mare Nostrum 4, in this case, ARM high power seems to have a slight performance advantage. If we zoom in to have a more accurate viewing of what's the performance difference, we can see here on the 3 rightmost images, again, ARM low power, high end, and the Mare Nostrum equivalent, that we can see these also have the same time scale, but they are zooming. This is at the beginning of the second iteration here, that would be more or less this. And we can see that most phases, not to say all, are sped up from the ARM low power to the other 2 equivalents, and the difference between ARM high end and Mare Nostrum are very, very small, as we saw in the zoom in, but in this case ARM high power wins. And to just show a bit all the data, we can also go back, and we have here the generate HPCG comparison. It's a different script to generate a different speed up, and it's also on the slides, but the image that we would generate is this. Everything scaled to the base values, the Mare Nostrum 4 performance with 1 core per MPI, and we can see the speed up of the different configurations. We can see that ARM low power begins with 20% of the Mare Nostrum performance and scales nearly to 35-37%, but it plateaus relatively fast. And the other 2 have maybe the similar curve, but they have higher speed up. And this speed up is so low also, again, because we are running a extremely small input benchmark in order to be able to run the simulations fast for the tutorial that we usually run. Welcome. So this is all the 3rd video. I try to make it way faster because it would be repeating the same thing over and over and over again. Just, well, let me change to this slide. Just a little remark that these results are not the ones we usually use. It's like trying to assemble all the simulations to give a general result to show in the tutorial, but we use other data. And also with the Paraver view, we can not only see the status and the time duration of the different phases, but we can also plot different hardware counters, L1 catch hit ratio, miss ratio, the DRAM bandwidth, all the PAPI counters that there is in the specification. Most of them we can generate in the simulator, and we can view and analyze with Paraver, either for the whole merged simulation or for every computational phase simulation independently. Okay.
There is a question for you, Francesca. Yes. I will read it out from Jack Jones. Given that you use trace files as inputs, I assume you don't have to deal with dynamic events such as branch prediction and pipeline flushes. Do you feel that not simulating such events has a negative impact on your performance design space exploration studies, as such events can have a large impact on the overall performance of a processor?
Yes, we know that it has an impact, but we are trying to concentrate on simulating the hardware characteristics that affect more the performance. And if we were to simulate a branch predictor, trying to simulate real hardware, none of us could do it. Well, our friends at ARM could do it because they know the hardware, but none of the other people here in this session can have any, not even close to the what real machines do. If we were trying to simulate Mare Nostrum, we don't know how the Intel branch predictor works.
Just as a side note, Francesc,
Yes.
Even though we use traces, I think we do have a branch predictor in task screen, right? And we can include one.
Yes,
It's
we
not a
got,
matter of not being able to do it.
yes, we could
It's a
implement
matter
it, but at the moment we don't
implementing
use
it.
one. But yes,
And we could get close to it, I guess. It's not like
yes,
we cannot do it. I mean,
yes,
traces don't think that uh, prevent us from having accurate
yes,
core models, even though it's not our goal here.
yes. I mean, yes, we could have it, but it's that if we were suppose speaking of abstract architectures, it will be fine, but then we couldn't try to compare against something resembling real world because we cannot predict real machines unless we have the information. Regretfully, we do.
Okay, Frances, as your time is up, I suggest we go on. You have a
Yes.
quiz now?
Yes.
Okay.
Okay, let me switch to, it's here the code, but let me switch to the browser because I have everything open.
Yeah.
Ah. Oh, okay.
Okay, so we're using Menti again. I gave you the code in the chat.
Yes, it's also here on the top. Okay, and I will wait a little bit and then I will start the countdown. Nice.
I think you have a number of people connected
Yes,
already. So
11. Yes, we can start. Oh.
okay, what type of application does MUSA support?
Yes, it's only shared memory, only distributed, or both. And yes, 10 people got it right. We support hybrid applications that use both MPA and OpenMP. We could also support applications that only have one of both or of them. We support both. Okay. Oh,
Oh, yeah. Click on
yes.
present.
Yes. Okay. Okay.
You should have an arrow. Yeah.
Yes. I had not seen this. Okay. Now the second question. Ah. When do I need to trace an application again? When changing the number of simulated cores, when changing the number of MPA ranks, or when changing the architectural parameters? Okay, time's up. Let's see. Oh, very distributed
Uh-oh.
this one.
This one was harder.
Yes, I have repeated the MPI plus OpenMP a lot of times, but I don't think I repeated this one enough. Yes. Now let's see the leaderboard. Uh-huh.
Mm.
Yes. Okay. Now let's see what do we have next. The third question, and last. Does MUSA take into account runtime events such as task scheduling across threads? Yes or no? Simple yes or no. Okay. Time's up. Let's see the answers. Oh, distributed these two. Yes, at least more people got the answer
yeah.
right. That's nice.
The majority got it right.
Yes. Yes. Yes, we do take into account task scheduling, all the related events, task creation, task weights, dependencies, and Nath is the winner.
Well done,
Yes.
Nath.
Yes. And I think that here last we have a feedback question from what you have been able to see from the videos that usually is not much. What do you think of MUSA? Is it intuitive to use, or does it seem intuitive to use for you from the tutorial? Would it be a useful tool for you, you think? And would you like a public release of MUSA? That's something we are working on at the moment. I think some of all of our partners on the EPI project have a public release that was made some time ago, but well, a private release that was made, but not a public one. Okay, this is nice. We will keep the results for later. I think that yes, we need to work a little bit on the intuitiveness.
Yeah.
Yeah,
That's what I was going to say. I'm glad you said it yourself.
No. I am aware that it's been a little bit, a lot of information, very dense, even if some of them were very repeating. I know some of it's very hard to understand until you have tried to do it yourself.
Okay, but you definitely have to make it a public release.
Yes, people want it. We've been thinking of it. We have to clean up a little bit the codes and the comments, and then we'll make it in the near future. Yes, it's the end. Okay, I don't know if you have time for a little bit more conclusions. No, we are over. So just thank you all for coming and enduring my presentation. And I hope the rest of the presentations are not so dense and are more agile and happy.
So are you done, Francesc?
Yes, I'm done.
Okay. Well, thank you very much. Actually, we only have 2 minutes left in the break. Yeah, this was a coffee break. So we will keep to the original timing. So 2 minutes break, and then we start again in 2 minutes with your first steps into Gem5 by Gregory and Joel. Gregory and Joel, get ready. You start in 2 minutes.
Yes, we are.
Okay. Thank you.
Yes.
Hello, everyone, and thank you very much for joining us today, and welcome to this Gem5 First Steps session. Before we get started, I would like to invite you to go to menti.com and please help us to answer to the first question that will allow us to better understand the audience today. Basically, the idea is to capture the level of the audience. So
give us some time to connect to the new number. So it's, yeah, you must click on present. Yeah, that's it.
how much do you know about Gem5? Are you a beginner, an experienced person, or would like to get to know you?
So what is the number? 45.
4532894.
So let's see.
Okay, so let's see.
How many people is already? Wow.
Well, they're not really beginners, are they?
No. Okay.
Okay.
3. So this is a medium scale. That means that we have an audience with some skills on Gem5. The idea for us today is to give you a short introduction on Gem5, and the hands-on session will be driven by Gregory later. My name is Wanza Joel. I'm head of simulation at CPER, and Gregory Vomorin is from Atos. I don't know, before we start, Gregory, would you like to say a few words to the audience?
Yeah, I'm working in Atos, and I will be talking a bit later when we will do the hands-on sessions. Yeah. Talk to you later, guys.
Yes, and personally, I've been involved in many Mont-Blanc projects, Mont-Blanc 2, Mont-Blanc 3, and now Mont-Blanc 2020. And I'm happy to share with you today Gem5, because we've been using this tool from the beginning, and we saw it growing in terms of activity and the community as well. So the outline for this session this morning, in the next slide, Craig, is, first of all, I will give you a short introduction of Gem5. Then Gregory will take hands-on session so that he will show you how to download, compile. Probably you must know some of this, but he will also share a small demo of what kind of exercises or experiments we can play when using Gem5. Then I will come back later to introduce you recent features on Gem5. So what is Gem5? Gem5 is an open source computer architecture simulator. It is a modular platform for computer system research. Today, it is well used by academia institutions and also by computer vendors. It is possible in Gem5 to run full application, including an operating system. And there are multiple architecture that are supported, such as x86 or ARM, even RISC-V. But from the original, Gem5 is a merger of two university projects. At the University of Michigan first, you had this M5 project where the objective was to model the network, including TCP/IP networking protocol. And almost at the same time, we also had this GEMS project at the University of Wisconsin, where the objective was to characterize and evaluate the performance of multi-core hardware systems. So in 2011, there was a merger of the best part of those two projects that led us to Gem5, and we had this first paper made in 2011. So this is a bit how Gem5 started. But before we go more into details, it's always good to remember to remind what is the level of abstractions when it's about modeling. There are many abstraction levels of details when you are architecture trying to understand the a taken design. For instance, there are hardware virtualization. This is where mostly you don't have any timing and you want to emulate instructions. Generally, you have the same type of instruction set between the host and the guest. The advantage of this level of modeling is that you can simulate up to giga instruction per second, while if you would like to have more architecture models, generally people move to behavioral mode. So in behavioral mode, you have tens of maps using simulation tools such as QEMU, but Gem5 can also operate in this mode. Generally, the models are loosely timed. You have some behavioral models such as caches, buses, and if you would like to go for performance extrapolation or let's say evaluation, you can use the timing mode. In the timing mode, you have most of the timing at CPU level or memory subsystem as well, and some advanced on-bounder that allow to go up to performance extrapolation. This is generally where Gem5 is used. You have few maps that can be executed. And of course, if you want to make more detailed modelization, generally this is at gate level where you can have the full out of order and order CPU models. This is RTL simulation. In Gem5, it is also possible to go in a detailed mode where you can, the simulation is a bit slower, much more slower, because it's always about the trade-off between the speed and the precision. But if you want to go to details for some very few problematics, it can be useful as it responds to the accuracy maximum. So next slide. What are the reasons and when to not use Gem5, and when to use it? Generally speaking, Gem5 is not used for performance validation. Performance validation cannot be done in Gem5 because generally you don't have a specific model or IP running in Gem5. The models or devices components are generic, targeting a specific instruction sets, but they are not a specific product that can be on which the performance validation can be done. And you don't use Gem5 for core microarchitectural exploration. This is not the purpose here. Mostly it is for research. And of course, we cannot use Gem5 for design correctness. To verify a design, generally you have RTL, a design code, and some design under test and test bench. So those are mostly RTL design process, but we can use Gem5 to run real workloads for a target for an instruction set that you want x86 or even RISC-V. Of course, we can also use Gem5 for early prototyping. This is generally the case when you start a design project. You don't have yet the RTL, you don't have yet all the stuff together, but Gem5 can help you to make a very early virtual prototyping so that you can start some exploration. And of course, at system level, as Gem5 is capable to model a kind of motherboard where you have components such as memory DIMMs and so on. So Gem5 is also good for that. It provides better system level insight. As I said from the beginning, in the next slide, Gem5 is an open source community, and this community is very, very active from the beginning. Here we have some statistics of July 2020. You can see in terms of citations and in terms of the commit that has been done at the Git project, it was increasingly growing year after year. That show you how much the community is active, and even the research domain as well. You can see in terms of publication per year, there are hundreds of publications that include work on Gem5. So that's it on my side, a small intro. Most of the things I've said, you might probably already know it. So now it's time for hands-on session with Gregory. Thank you.
Thanks, Joel. So hello, everybody. So just a few things before I start. So at first we wanted to do that live, so we could do that with people in the room, and so people could follow the progress with me. But now, since I am online, so we decided that so we are not expecting you to do the stuff that I will do at the same time with me, right? I will just show you. And for me, the goal is not like for you to be able to run Gem5, but just to give you some material. So after that, you can look at the presentation and you can do all what I will do now, and so you can repeat on your own, and so you can start playing around with Gem5, right? So please bear with me because this is a difficult exercise to do like a tutorial online. So without people in the room, so I cannot really follow whether this is okay for you guys. So please ask questions on the Zoom chat if I am going too fast and stuff like this. Thank you. So the first thing when you want to use Gem5 is just to first to get it and to compile it. So this is Gem5 is open source, so you can get it at this address. And then in order to compile it, I have this command line here. And so you can scons, this is a build system used by Gem5. This is working like make or CMake, right? If you are more familiar with this. Then you have this, which is the executable that we're going to generate. And so in this executable, we in the past, we mentioned the ISA that Gem5 is going to be using. So now we are going to say that we are going to simulate ARM architectures. And then we have like finally this parameter of .opt, which is the version of the executable that we are going to compile. So you have a choice between optimal, perf, or fast. So most people use opt because this is all of these parameters are just a combination of flag optimization parameters, and whether it includes debug symbols into the executable. So yeah, I would recommend for you to always use opt in this case. So let's see if I do that. So it's a bit long to compile, so I will not do it live. I will just show you the results. So I recorded my terminal. So I hope this is big enough for you, so you can read. I am creating, and then I'm cloning the project, Gem5. So it takes a bit of time. I've already have all the dependencies on the laptop. So if you want the list of all the dependencies, you can find them on the Gem5 website. So I haven't included that part here. And yeah, I'm running on Red Hat 7.5 as well. Just so that you know. Okay. And so we fetch Gem5, and now we can compile it. So I'm just checking out to the commit that I want. So I'm pretty sure of the version that I am compiling. And then I am compiling with the command line that I detailed you before. And so now we are gonna run for like around 8 minutes on my computer. So I will skip a bit because it's not really interesting. This is just compiling outputs. Just to show, this is just to show you how simple it is to start and to compile, right? Okay, just compilation output, and then at the end we generate our executable, which is the arm/gem5.opt. And that should be good. Okay. So so now we have Gem5 compile. So this is the first step if we want to use Gem5, right? And so the second thing is now so what we want to do is to simulate a simple benchmark, which so I went for the stream benchmark. I don't know if you guys know it. This is pretty standard. It's composed of 4 simple kernels, which are simple array operations. So for example, the first one is just array copy, and I'm just multiplying an array with a scalar on the second one, and so on. So this is very simple operation with arrays. So it's good benchmark to test the memory bandwidth of your architecture. Okay, and so I want to simulate. So first you need to cross-compile this benchmark for your targeted architecture that you want to use with Gem5. So targeted architecture in this case is ARM v8. And so the architecture that I want to simulate, so one of the reasons that you would want to do that is, so I have this benchmark, I have this code, and I want to know how it will behave on this new architecture that I don't have. So it can be for multiple reasons. Like I want, maybe the architecture is not available yet, it's too expensive, or maybe I want to modify a bit the architecture after that. So Gem5 will allow you to play around with the architecture beforehand. So and I can also do software optimization already on my code. I can see if my code is running, and I can try to optimize my code beforehand, for example. This is a few reasons that I would want to do that, to simulate this code with Gem5. Okay, so we're not gonna go that far as simulating all the Exynos architecture because this is quite complex, but at least I will show you the few steps to get there, the first few steps at least. So the first questions when you want to simulate with Gem5 is whether you want to do syscall emulation or full system. So the difference between the two is that syscall emulations, you don't simulate the operating system, you are just simulating the applications. So when you want to do that when this is simpler to do, and so you are not simulating all the OS stack. So when system level timing are not important for you, such as TLB or device accesses. And on the other hand, you have the full system emulations, where you actually run the full OS, a full Linux. And this is more expensive to do because it requires more data. Like you need to have a disk image with the operating system installed. You need device tree files. You need to provide that to Gem5. So this is slower, but also more precise. So we are always in this speed versus accuracy of the simulation. So and so to do these two types of operations, you can do that with Gem5 because config scripts are already available for that. So in our case, we will go for syscall emulation for our tutorial because this is simpler. So I can show you how it looks.
Gregory, sorry, can I interrupt you for a question because it was actually about the previous slide. Very
Sure.
simple question. Is there any plan to support Cortex R52 and newer Cortex R chips?
That's a good question. That you should probably ask to ARM people. I'm not really sure how much of the there are already some models available in ARM. The A72. I've seen some models. I'm not sure they are open source or
Well, we can ask our ARM friends this afternoon because we have the ARM team, or they are here, but they're probably listening. So prepare your answer, Richard and Javier.
What I can add is that generally the CPU model are generic, but if you are targeting a specific one, you can get in touch with processor vendors such as ARM, so that if they have any planning for providing a specific product or CPU, they can do so and share with you with some confidential and disclosed agreement.
Okay, so I will put this question on hold, and as soon as Richard has the answer, or Javier, I'll give it. Okay?
Yeah, thanks for the questions.
Good question.
So now I am in the same machines that I've shown you that I compile my Gem5 on, right? So the first thing I will do is just to do a very simple first launch, just to show you guys. So I have the executable that I've launched, and And so I'm using the default config script for syscall emulation, so se.py, which go for syscall emulations. And then I have my benchmark stream that is compiled for on. And so I will never execute the command lines because they can take some time. I will just show you the output. I've already launched it beforehand. So the output would look like this. Oh, sorry. It will look like this. So this is the result directory. So you can see two main things. The first one is a config files that contains the architecture that I've simulated. So this PDF is shown here. So this is just a basic, the most simple architecture that you can do with Gem5, which is just a simple CPU, which is an atomic simple CPU. So the simplest CPUs you have on Gem5, connected through an X bar to a memory controller, which is in this case DDR3. Okay, so this is the simplest architecture, and yeah, so I have the output of my simulation. So sorry. Yes, so here we find again the command line that I've typed. So we can see that my benchmark executed. So this is output of my benchmark there. So my benchmark is collecting some matrix. So yeah, just to see that my simulation went okay. And now there is also the last file that I want you to look at is a stat file, which is a output statistics. Which are shown here. So we have a bunch of statistics. So for example, we can see that our CPU committed some instructions, so 1,500,000,000 instructions around that. So we can see, for example, the classes of operation that my CPU executed. So we can see like it execute a lot of integer operation on integers, which is expected based on the benchmark, right? So almost half of the instructions that are executed are operation on integers. And so if we go there, we can see that the remaining operations that I've done is just fetching and writing to memory. So it makes sense based on the benchmark that I am executing. Right? So it was the first executions. So let's go back here. Okay. And so I've explained this. Just to explain a bit how Gem5 is working. So you have C++ classes in Gem5 that represent the models of everything in Gem5. So it can be an ISA, it can be a new hardware accelerator, and all of these objects inherit from a single object, which is a sim object. So you can always add your own models into Gem5. If you want to have a new CPU model, for example, you can always add it to Gem5. And then on the second half, you have config scripts, which are Python scripts. And so, for example, in this case, in Gem5, you will find a model of cache, for example. And then with Python script, I can instantiate L1 cache, a specific cache, which have these specific parameters. And I can instantiate this and connect to the rest of my simulations. And also with Python script, I can control, I can start, I can stop, I can checkpoint my simulations. So, yeah. So you have two separate things, right? Maybe this. Okay, so if we go back to our benchmark and I want to add caches to my benchmark, because now I don't have any caches. So if you want to simulate memory hierarchy in Gem5, you have two possibilities. You can go for the classic models or the Ruby simulation, Ruby modeling, sorry. So the classic model is simpler and faster than Ruby. And this is, you would want to go for the classic model if you don't have a lot of complex interaction in terms of coherency protocol, interaction between caches, for example, or if you don't want to have a super accurate model of the network on chip, right? Because Ruby is very good at this, right? Simulating the network on chip, simulating the coherency protocol. So you have a choice to do that. So for us, our benchmark is even though it can be made parallel, you don't have a lot of problematic of sharing between caches, right? This is all stencil. Every core is accessing their own data, going through their own cache. There is not much sharing in this case. So I will choose to go for the classic model, also because this is faster to run. And so, yeah, I would just to challenge you a bit, guys. So this is my benchmark code that I want to run with caches, and I'm just wondering whether you what will happen to my performance if caches are added. Do you think that cache are not going to help because there is no reuse at all in my benchmark? Do you think that only L1 cache helps, or do you think that both of my, if I have a two-level caches hierarchy, do you think that L1 and L2 caches both are going to help the performance? So I'm just assuming that this is basic assumptions that array are not fitting in my cache, and that the cache size are pretty standard compared to what already exists. So this is a bit difficult, but yeah, just to challenge you guys. What happened here? Maybe I should. Yeah, I guess I should put the slide there, right? Yes. Okay. So I don't know if you guys can vote here. Is it okay? Is it working?
Let me check.
So I have 1 answer, 2 answers. Oh, okay. Okay. So, okay, so let's say I'm not going to give the answer right now. So let's see how it goes with Gem5. So I will take the same simulation that I've shown you, and I will just add caches to my simulation with the classic model, like I explained. So you just need to add command parameters to the command line. So we find the same command line I've shown you before. I'm just adding this parameter and then configuration for my two-level caches hierarchy. So very standard parameters, 1 megabyte cache for L2 and 32 kilobyte for L1 data cache and L1 instruction cache. So let's see the results. So you can see the architecture. So this is the same architecture that I am simulating. I've just added caches to this. So we can see, so this was the first architecture, and then we just added the L1 and L1 caches that are connected to the crossbar to the L2 caches that are connected to the crossbar to the memory controller. So pretty standard, right? This is. And so let's see how it goes in terms of results. Now in my statistic, I can collect statistic about my instruction cache and about all my caches actually. So let's see how it goes. So this is the overall miss rate for my instruction cache. Yes, this is so this is overall miss rate for my data cache. So I have a miss rate of 12%. So I have a lot of reuse in my data cache because there is a reuse at the cache line level. There is several data per cache line, so it makes sense. So L1 cache is definitely helping because I have a decent miss rate there. And then let's see about my L2 cache. So my L2 miss rate is around 100, almost 100%. So there is no reuse at all in my L2 cache, right? So yeah, the answer here, the correct answer was this one, right? So yeah. Okay, so okay, let's go back to the presentations. Okay, so very simply, I've added caches, and so for some more improvement, so now this is a simulation that I have, a very simple model of CPU, a very simple model of memory, and now I want to complexify a bit just by switching models. So I want to go to 4 ARM core and out of order core and some DDR4 controller, for example. And so Gem5, there is already a lot of models implemented into Gem5. So there is that you can already reuse. So there is a lot of different ISA that you can model. So they are not all fully supported. The most compatible ones are the ARM and the x86. You have a bunch of CPU models that you can specify for your own needs. So you have in-order cores, you have out-of-order cores, you have KVM. All those models are connected to the same and single port interface. So to simulate the cache hierarchy models, I've explained the difference between the Ruby and the classic memory models. So you can see that, for example, for the Ruby cache models, I have the choice between several coherency protocol implementations. This is the same. I have a bunch of DRAM models that are already implemented. I can go for DDR4, I can go for HBM, and so on. I can also simulate GPU inside Gem5. Yeah, and disk device such as PCI or disk. And I can also connect to external simulators such as DRAM sim if I want a more accurate representation of my DRAM, for example. Okay, so now that we know that we have this bunch of models, so let's try to actually do this just by playing with parameters. And so this will be my last command line. So I'm just increasing my command line by a bunch of parameters. So I have my caches parameters. So now I am specifying the size of my memory, and I'm specifying that I want to use this model that is available. Yeah, and yeah, I specify the number of CPUs, and I said that I want to use this out of order model of CPU. Right. So again, very simple, and you can just switch parameters with the parameter. You can just switch the models that I want to use by using command line parameters. So this is very simple to use if I don't implement new models, right? It was just to give you that idea. And so for the same thing, we can see the architecture that we are simulating in this case. So this is the same thing as this one, just duplicated with 4. So we have 4 CPU. I'm not sure how clear that is, but we have 4 CPUs with caches, CPUs that are modeling with that are out of order, that are connected to an L2 cache, yes, and L2 cache, and then connected to the DDR4 controller. So yeah, this is what I wanted to simulate. So, and so if we look at the results, I can check for every CPU. I can check how many instructions it executed and so on. In my statistic, it just added the statistic for all the CPUs, right? Okay, so yeah, I'm going to stop here for the complexification of the simulation. So I just wanted to show you how to use Gem5 with the configuration file and play around with parameters and models. Just one last thing is that every time I've added parameters to my command line, I have complexified my simulation. So it comes with I am paying more simulation time. So of course, the number that I am giving here are not are only representative for my benchmark, but this is a good thing to keep in mind, that more complexity means more simulation time, of course, but yeah, just some numbers to give you this idea. So I just want to ask, so when there is a 10,000 slowdown of execution going to just by using Gem5, right? But even if this is a very simple run, then by adding caches, I'm adding 12% execution time, so pretty decent. But yeah, when I'm using the out of order model of CPU instead of the cache, I am paying 10 times 9 simulation time. So this is very expensive because the model is much more precise, and so it takes a lot more time. So just to make you aware of that case. So if you can go back to Menti and ask for the last question. So by going from 1 CPU to 4 CPU, how much time do I? How much is the slowdown, right? So if you guys can go back to this, yeah. Is it working? Yes. Okay. If I start, then it should be. And then, so it seems like everybody voted. So can we see the result there? It was working last time. Sorry. We don't get to see the results. Come on. Sorry.
That's because you set a long timer.
We need to wait for the long timer.
Yeah, okay. Well, you know what? In the meantime, I will ask you a real question that I got in the chat. Does Gem5 support also simulation of prefetch units?
Yes. So actually, this comes with a modeling of the memory hierarchy. So you can simulate prefetching with the classic memory models. With the classic memory models, I'm not sure that there is support for prefetching inside the Ruby. I think there is. Yeah, I'm not entirely sure. I think there is modeling of prefetching for both memory hierarchy. But yeah, it's difficult to play around in the Ruby because this is really integrated to the coherency protocol and stuff. So I know that you can play around with prefetching algorithm with the classical model. I need to check about the Ruby modeling. Yeah.
Okay, thanks. And we're nearly there.
Yeah.
In the meantime.
Oh, well.
And, okay.
Well, the majority got it right.
Yeah, I am actually surprised that nobody is complaining about how Gem5 is slow, because this is the answer that I would have picked. So okay, thanks guys, and so I give it back to Joel for the last sessions.
For the last part.
Yeah.
So thank you very much, Gregory. That was very interesting to see what kind of experiment and design feedbacks that Gem5 can provide. So now the idea is just to give you some, to talk about some recent features. When I say recent, mostly I mean what are for interest in the Mont-Blanc 2020 context. For instance, if we go on this next slide, instruction set is now supported, including 32-bit and 64-bit instructions. You can run almost all ARM applications, including an operating system, and everything is working fine now. If you'd like to perform some network on chip simulation, you can use Ruby. Ruby, at the beginning, it was working only for Intel architecture. Now it works also for ARM after a great effort done by several teams from Mont-Blanc project as well, and people from ARM. So this is a very good achievement that we can run full system simulation using Ruby in Gem5. It's also now possible to use ARM trusted firmware. ARM every 6 months provide what they call reference software stack, including this trusted firmware that allows to run more server-alike architecture in terms of modeling. So we are not just simulating systems that are suitable for embedded systems, but also for server design. So those kind of software are used. So it's quite good that we can use them now on Gem5. Also, there is this support of SVE for scalable, scalable vector extension. This is quite good. Don't miss the SVE introduction and programming this afternoon. There is a session. So SVE allows to run HPC-like workload with more operating floating point operations. If we go to the next slide, another feature of interest is distributed Gem5. Distributed Gem5 allows to run a small cluster of compute nodes. In this example, for instance, you can see we have 3 systems running in parallel on 3 hosts. We have simulated process 1, 2, and 4. What is good here is that this distributed Gem5 include NIC components for networking. You also have the switch router, so you can, for instance, simulate MPI transactions between different compute nodes, like in a real HPC cluster. So this is very interesting feature that is now available in Gem5. Of course, it is slow because of the sequential execution of each of the process, but it can help to make some experiment at cluster level as well. And what is also new is the support of RISC-V instruction set architecture. There are many implementation of the extensions that are supported, not all of them, but I can, for instance, notice that there is an extension A for atomic operation, extension F and D for single and double precision operations. We are few steps away to be able to run a full system. I mean, running an operating system RISC-V based on 39-bit virtual address. And of course, there is some translation look aside buffer components that allow to make the translation between from physical address space to virtual address space. So this is quite good. RISC-V is now being usable in Gem5. This is also one recent feature. And the last one, and not the least, not yet. We also have the support of System C. This is good because you can co-simulate Gem5 with some models that you have done or created using the standard GM System C TLM. So there is an overhead of about 8%, but the interesting part is that the System C is running on its own kernel, and that you have the interaction between the two systems. You can have a part of your system running in Gem5, while you also have another subsystem running in System C. They can interact together. You have one paper cited here where we took this plot for illustration. So this is also interesting. And the latest feature that has been integrated is this ARM transactional memory extension support in Gem5. Mostly transactional memory extension is done to address the multi-threading concurrency. If you remember the tutorial this morning about MUSA concurrencies, when you manage multi-threading workload, is a very interesting topic, because this is where you can increase the performance, where you can save by simply the way that you are programming. So compared to the standard way of synchronization management, you have the log-free, the fine-grained locking, or coarse-grained locking. HGM, for hardware transactional memory, is supposed to give a higher performance and scalability with less complicated algorithm. This is what ARM says. You can see for more detail in the link here. But it is very interesting for that we can use it today in Gem5 as well. So that is a bit talk about what are recent in Gem5 and that we saw interesting to present. Thank you. Gregory, if you would like to say a few words before we conclude our session. And
so just to so if you have some questions, please ask them on the Zoom chat. So just as a reminder, so what we've done during this hour is fetching and compilation of Gem5, run some experiments with the default config script that are already available, and so I've played around with Gem5 model and we detail a bit some recent features of Gem5. So yeah, just as a reminder, everything that we've shown there, all the slides and the scripts that I've shown are going to be available on the Mont-Blanc website later. So yeah, don't worry if you didn't catch up everything going to be available online. And hopefully it was helpful even for people that already know Gem5 a bit, even though it was most targeted for Gem5 beginners.
We hope so. Thank you very much for.
Thank you very much. So we don't have any questions. So I guess this is time for lunch, right?
Yeah, you're done. Okay. Oh well. Oh, wonderful. Okay. So yeah, indeed, it is time for lunch. I had a specific slide for that. Let me check. Yeah.
Okay. So do you want me to stop sharing? Okay.
No, I'm the boss here. I can stop you sharing. Okay. So I would like to thank all. I don't have questions in the Q&A tool for you, so we'll wait a few seconds. But anyway, we have a lunch break now, big lunch break to allow you to attend the HiPEAC keynote. But we hope to see you all again at 3 CET. The afternoon will be dedicated to SVE with an introduction, some programming tips, and a Gem5 SVE hands-on. So I would like to finish by thanking our speakers for this morning. Thank you to Alejandro, to Francesc, Adria, Gregory, Joel. Thank you for sharing all your experience with the Mont-Blanc tools. And as I said, we hope to see you all again at 3 for an introduction to SVE and then more about SVE. Any questions before I stop? I don't see any questions, unless you're sending them in the chat, and I don't see the chat for the moment. Okay, well, I will, if you think of questions later, remember we're back at 3, so you can ask them later. Thank you, enjoy your lunch, and see you later.
Thank you.
You can just start recording now.
Done.
Perfect. Hello, everyone, and welcome to the next session in our workshop. This is going to be about ARM SVE, a quick introduction to the new instruction set. Well, not so new anymore. I'm going to show you a video of one of our HPC directors explaining the extension to you. And I will stop it at a couple of points during the presentation so I can ask a couple of questions. These are going to be mostly self-assessment questions. Just if you respond correctly, you can be certain that you're following and keeping in mind like some key points that some people overlook because this is quite a different thing, this SVE. So this is the Menti code. I hope it's pasted in the chat as well. So feel free to join there, and I will direct you to the questions when it's time. And without further ado, let's start.
All right. Well, hello, everybody. My name is John Linford. I'm ARMS Director for HPC Engineering, and I want to give you an introduction to ARMS SVE technology. SVE is ARM's Scalable Vector Extension. This is a vector instruction set architecture. It's a feature which our silicon partners can implement in their CPUs. And there's a lot of design flexibility around SVE. One of the defining features of SVE is that although it's a vector instruction set architecture, SVE itself does not have a defined vector length. So you're probably familiar with vector instruction architectures that do have a defined length. Most instruction architectures like ARMS Neon, for instance, will specify that vectors must be of a certain number of bits, usually 128 or 256 or maybe 512 bits. SVE takes a different approach. In the very definition of the instruction architecture itself, there is no definition of how wide a vector should be. And this creates a completely new paradigm for programming vectors in a computer. It's really a different approach to doing vectorization overall. And to get an idea of how this works, let's take a look at a sort of a high-level view of SVE and how it's implemented. Essentially, the hardware specifies the vector length. At some point, you have to have a number of bits in a vector. This is essentially the width of the vector registers. But although this is defined in the hardware, the software has no concept of a length of a vector. In software, vectors have no length. And so the instructions you issue to the hardware are very abstract. They say things like, take vector A and vector B, add them, and put the results in vector C. This is a very different approach from saying take 512 bits of A, 512 bits of B, and take the 512-bit result and put it in C. In this case, we're taking an abstract view that A and B are vectors, and SVE simply doesn't know or even care how many bits are in that vector. The result is the exact same binary code can run on architectures with different vector lengths. So I can take exactly the same instruction and without compiling or doing anything, run that binary code on one architecture which defines vectors to be 512 bits, or I can run it on an architecture that defines vectors to be 256 bits. Now this alone is pretty cool. It allows for a higher degree of portability, and it really enables better vectorization and enables a programmer to think at a higher level. You're not really concerned about the implementation details of your vectorization. You can start to think more abstractly. In addition to taking a vector length agnostic approach, SVE includes a set of features that are designed to help improve auto-vectorization of complex codes. It has instructions for performing gather, load, and scatter store. So vectorizing across arrays of structures of arrays. So these more complicated data types that are more common in real world codes. There's a concept of predication, which we'll be covering at length here, that allows you to map operations onto different lanes of the vectors in a way that's much more powerful than you might be able to with something like a bit mask in another architecture. There's also a powerful feature called software managed speculation, where you are able to vectorize code before you actually know the upper bounds of what's safe to vectorize in your data. And then there's extended horizontal reductions that will let you do math operations across multiple lanes of this vector within the register itself. So not only across multiple vector registers, but in a single vector register, doing lane-to-lane operations. Now, I just said the words vector length agnostic, but what does this really mean? This is, as a programmer, this is a mindset. It's a programming model where I neither know nor care what the length of my vector in fact is in the implementation. Taking a vector length agnostic approach enables you to write your code once, compile it once, and then run it on any architecture that implements SVE. You don't care how many vector units are there. You don't care how many bits are in a vector register. The code simply runs. This also allows you to vectorize more loops. Taking that piece of the implementation and abstracting it empowers the compiler and the programmer to vectorize more efficiently. We'll see how in a minute. So I want to take a look at vector length agnosticism and sort of walk through it and compare this to a traditional fixed width instruction set architecture. Let's do an example where we compute data that has 10 chunks of 4 bytes. So we're going to do an operation on 10 chunks of 4 bytes. Now, if we had a scalar architecture, we would do 10 iterations over a 4-byte register. That's one way we could go about this. So we could think of this as doing 10 little shot glasses of work. With a familiar fixed width instruction set vector architecture, we might have, let's say we have a vector width of 16 bytes. Then we could do 2 iterations over the fixed width 16-byte vector register. And this will leave a small remainder of 2 4-bytes of data that we still have to process. So we have a main loop, which is vectorized, and then we have the drain loop, which is scalar. This is a very common pattern. It occurs on any architecture that implements a fixed width vector instruction set. A vector length agnostic approach says we use the same code regardless of the actual pieces of data that are being processed. Using a 16-byte vector length agnostic architecture, we would do 3 iterations over the same vector register. But when we've exhausted the full width of the vector, so we've hit the last iteration of the loop and there's a little piece, instead of using a drain loop, we use an adjustable predicate to dynamically resize the vector width. Now this is different from a bit mask because a bit mask would compute all elements of that vector and then throw away the pieces you don't need. This is actually telling the hardware, only use the piece of the vector register which you need. And having that ability to dynamically resize and predicate in the remainder both reduces the size of the binary code by removing that drain loop, and it opens up the possibilities of doing more interesting things in hardware optimization, basically turning off pieces of hardware that we don't need when we don't need them. Now, how big can an SVE vector be? I've told you it doesn't really matter how big it is, but are there limits? Yes, in fact, there are. So SVE vectors can be any multiple of 128 bits all the way up to 2048 bits. So 384, that's a perfectly valid vector width in SVE. Typically, you'll see something like 128, 256, 512, but it's possible to go all the way up to 2K bits. Now, even when you know, let's say you're a programmer and you're working on an architecture and you know for a fact that that architecture implements SVE and it implements it in 512 bits. For example, maybe you're working on the Fujitsu A64FX, which implements SVE in 512 bits. Even then, you should not assume that you know the width of the vector when you go to write your code, because the width of the SVE vectors can be reduced by the operating system or the hypervisor if that's deemed to be beneficial. So even if you know the hardware implementation of SVE on your platform, at runtime it might not be fully available to you for whatever reason. So you should always take a vector length agnostic approach when you're working with SVE, if at all possible. Generally, you'll get the best portability, get the best stability, and in many cases, you get the same performance as you would out of a fixed width implementation. You might actually get better because you'll get more vectorization. Now this raises some really interesting questions. If I don't know how big my vectors are, how do I start chunking data through my vector pipeline? How can I program if I don't actually know how wide my vectors are? Well, SVE provides features to enable this paradigm. Core to the SVE implementation is this idea of a predicate. Predicates map operations to lanes of the vector. This is essentially allows us to say that only certain pieces of the vector are active. And along with predication comes a suite of instructions which allow us to query and dynamically calculate vector widths based on other factors. So I can do things like striding over an array by my vector width in a single instruction. The instruction tells me how large the vector width is dynamically at runtime, and then I can use that to increment my loop counter as I move forward in a vectorized loop. There's also an ability to do speculative vectorization, where you attempt to load a piece of data, and if, let's say, half of that vector lands in a protected memory region, and so therefore it's not readable, instead of raising a fault, what is returned is a predicate telling you the valid vector lanes. So this lets you probe your data in a sense and figure out how far does the data go, so that I'm not vectorizing beyond what's beyond a valid address and into a protected region. So there are ways to handle this, and it actually, once you start thinking about your data as some multiple of bits, but you start thinking about it as a collection of vectors of unknown length, it becomes a very natural way, I think, to program. Now, fortunately, you often don't have to think at that level at all. The compilers and libraries and tools and debuggers that are currently available, both commercial and free, open source, support SVE very well. And they take advantage of SVE's features to auto-vectorize code using things like the gather, load, and scatter store instructions. I've had some fun with this, where taking complex arrays of structures, and even structures of arrays, twisting them around and trying to trick the compiler into generating silly code. And I'm often impressed with how well the compiler is able to generate strided and structured load instructions to pack the data efficiently and vectorize it, even for very complicated types. So it does work pretty well. Don't take my word for it. Do try it in hands-on. What I'm basically telling you is don't panic. If you see vector length agnostic programming and you see that this is a new instruction set architecture with a new paradigm, don't worry. A lot of the hard work and the heavy lifting is done for you automatically in the compilers that are out there. Open source compilers like GCC and LLVM support SVE and have done for coming on to almost a decade now. The ARM compiler, Cray compiler, and Fujitsu compiler are all commercial offerings which support SVE today and do a very good job of auto-vectorizing, especially for HPC and scientific codes. There's also a number of math libraries out there that natively support SVE. And if your compilers and libraries aren't cutting it for you, there's a suite of compiler intrinsics, the ARM-C language extensions, which is supported by many of the compilers I've listed here. This allows you as a programmer to find a nice middle ground between coding raw assembly and using our higher level language like C or Fortran. Now, it's always possible to go straight to the assembly, and I'm always impressed by how clean the assembly for SVE is compared to some other fixed width instruction set architectures I could mention. It's actually not that painful to program SVE assembly. I definitely don't recommend it as a first start. Do please try auto-vectorization and the libraries and the intrinsics first. But if you ever do find yourself in that situation, I find it's not so bad. Hopefully you never will be. Compilers are pretty good. I mentioned the open source supports SVE for coming on to almost a decade now. It's really has been part of GCC since early 2016. And we've been fully supported in things like bin utils since 2017. So we've even had full official support in these very well-known popular tool chains for quite some time. So it's not only well supported, it's actually approaching a point where it's very stable as well. So Quick recap before I go on to some more detail here. SVE enables vector length agnostic programming. This is a new paradigm, a new way for approaching programming where you don't know or care what the vector length is. You simply think of your program as a collection of vectors and move forward from there without thinking about it as a collection of bits. VLA will enable better portability, more scalability, and optimization because once you stop thinking about the implementation of your vector instruction set and just think about it abstractly, you can move between different hardware that implements the SVE registers at different widths. Predicates are a central idea to SVE. The predicate enables you to map operations onto vector lanes and dynamically activate or deactivate vector lanes. This allows you to control the vector width. Remember that example where we have a drain loop and we want to dynamically resize the vector down. This is exactly what you would do here. You would use your predicate to turn off the inactive lanes in the final iteration of your vector loop, and therefore you don't need a drain loop. The actual vector length is always set by the CPU architect. It's a multiple of 128 bits, and even though you might know what it is in the hardware, you shouldn't take that as a hard assumption because it can be dynamically reduced by the operating system or the hypervisor. At the end of the day, your best bet is to take a vector length agnostic approach. Don't try to guess what the vector width is. Don't make assumptions about it. Just stay in a vector length agnostic mindset. SVE was designed for HPC. It was specifically designed for supercomputing and scientific computing. And the first implementation of it was the Fujitsu Fugaku supercomputer at Riken in Japan, which you see behind me. Unfortunately, not actually behind me. There's just a picture, of course. But this system is the first large-scale deployment of SVE in silicon. And it's designed for scientific computing. It is the Japanese national computing instrument. It is hardcore HPC. So if you're coming from that background, you'll find that SVE very naturally maps to the types of problems you're trying to solve. And of course, many open source and commercial tools do currently support SVE. You'll have no problem coding SVE with the tools at hand.
So our first stop for a quick question.
Javier, we have 2 questions.
All right. Yeah.
You want
sure.
to have them now?
Yeah. Now works.
Okay. What is the cost of providing the abstraction in the hardware in terms of area, complexity, etc.?
Well, that's a complicated and involved question. That's going to depend on your architects. You can do whatever you want as long as you respect the standard. Even if I knew, I don't think I could divulge that information publicly. But
okay.
If you want, you can send an email with that question and I will try to reach out to the architects. It's going to depend on the chip, right? Different architects will take different approaches and different trade-offs. I can reach out internally and see if I can tell you, but not right now. Sorry about that.
Okay. Then another question from Timon. Why would OS/hypervisor dynamically downsize vector lengths?
That's, well, one possibility could be simply for efficiency. Right? If you don't need, say, if your machine supports all the way up to 2048 bits, but your codes won't vectorize properly, or they will waste a lot of lanes if you do it with such a width in your vectors, you might want just to, your OS might be able to, or the chip itself might be able to turn off pieces of hardware just because it knows you won't use them. Think also about saving states and that kind of thing.
Another reason is for in an HPC environment, you might want to migrate running programs between different hosts. So when you start a new program, it can be completely vector agnostic and run with any vector length you like. But once the program's already started, you'll want to keep that vector length if you migrate to a different host on your cluster that has a different vector length in hardware.
Okay. And then there was another, well, it was both a question and remark from Cristobal. It's a long one, but I really read it out for you. If it's too long, just maybe you can look at the question later. Why do you believe that ARM has limited the maximum vector lengths to 2048 bits? Since SVE was created to better address the compute requirements in domains such as HPC, where it is normal to find applications with very high DLP. In that sense, more traditional vendors such as Cray and NEC bet on long vectors, for example, Aurora Tsubasa, with an MVL of 16,384 bit. Longer vectors than 2048 bit would give us better performance.
Yes. My understanding is that the reason to limit the maximum size is for ABI reasons. You have to you have to set it somewhere. Even if the limit is insanely high, it has to be somewhere if you want to have to make sure it's compatible. That's one of the reasons they've given me. I don't know if Richard wants to add anything.
No, that makes sense as well.
Okay, thank you. Thank you, Javier, and thank you, Richard.
So the question that I wanted to ask was this one. And I think the discussion we just had kind of gives it away. But feel free to answer. I'll give you, I think, a few seconds and see how people. All right, so, okay. So let's call it. There's a few, just a few answers, but the right one is that one. So any multiple of 128 bits could be configured in your machine at runtime. So again, you cannot make assumptions about the size. Could be any of those. And now let's move back to the video and go with the second. Unless anyone has any more questions.
No, go on. We'll handle questions at the end.
Okay, perfect.
So I want to move into a little more detail now. Let's talk about how we work with SVE. What can we do to start writing some code? What are some of the considerations? Well, it helps to understand a little bit about SVE's registers. There are essentially three types of registers in SVE. You have the vector registers themselves. There's going to be 32 vector registers, which you don't know how wide they are and you don't care, but they're vector types. And they can be packed double precision, single precision, half precision, floating point, or packed integers of 64, 32, 16, or 8 and 8 bits. So you have 32 registers which store data, essentially. You also have 16 predicate registers. The predicate registers allow you to control the vector, control which lanes are active and to map operations onto vector lanes. There's a special predicate register called the first faulting register, and this is how we do software speculation. Software speculation, we'll look at it in more detail, is when I attempt to load a vector and then I set a predicate based on how much of that data is actually available to me. We'll talk about that in more detail in a minute, so don't worry about it too much. The thing to focus on here is that I have 32 data registers and I have 16 predicate registers. Generally speaking, the compiler will take care of all that for you, and you can code on your merry way. But the fact that we have to pair predicates with data means that we have to be cognizant of the predicates. That is a key part of coding SVE. Let's look at a little coding example here. This might help. So if we consider a simple SAXP, where we're taking a scalar times a vector plus a vector and storing it in a vector, and let's implement it in a simple Fortran code here. And first I'm going to do this in scalar. I'm going to take a piece of scalar code, and I've shown the assembly If you're not comfortable or familiar with assembly, don't panic too much. Just look at the side there behind the double slashes, and you can see a piece of pseudocode. The things to focus on are here. The B instruction, the branch instruction, marks the start of my loop, the I equals 1 through n loop. Within that loop, I first load I first load 2 pieces of data. So S1 becomes X at I, S2 becomes Y at I. And then I used a fused multiply add instruction to multiply my Xi times the scalar A, add my Y at I, and store the result into Y at I. The store back to Y at I is done in the next instruction here. And then we increment my loop counter in the x4 by 1 instruction, I plus equals 1. Then we do a comparison to see if we've reached the end of the scalar loop. If we have, we branch, or otherwise we leave the loop. So this is really not that complicated. Now I want to compare this to SVE, and what you'll notice is that it looks really similar. In fact, because we don't have a drain loop, and because we're able to think about our data as a collection of vectors instead of a collection of scalars, the resulting code structure is very similar. The difference is really just in the branch instructions and in the data manipulation instructions. So our first instruction here is while LT, and we're calculating a predicate. This is actually calculating which parts of the vector are active if I is less than n. So this is saying find those pieces of the xi array and the yi array for which I is less than n. This is going to set a predicate that would activate lanes of a vector for those vector elements. Then we are loading 2 vectors in the side of the loop body. So Z1 becomes a vector width of data from the X array. Z2 is now a vector's width of data from the Y array. Then we do again, a fused multiply add where I take a scalar times a vector plus a vector. And notice that in both the load instructions and the multiply instruction, we have this P0 parameter, which was our predicate. Every SVE instruction is going to need a predicate. Well, almost every SVE instruction. Most of the SVE instructions are going to use a predicate to indicate which lanes of the vector are active for that instruction. So I've taken 2 vectors up to the width of whatever is active in the predicate. I've loaded them into memory. I've multiplied one of them by a scalar, added it to the other one, and then I'm going to store back to the Y array, again, using the same predicate. So this is a very common sort of motif you'll see throughout SVE code, where we have the destination, the predicate, and the operands. Destination, predicate, operand. It happens over and over. And the predicate is the same throughout that whole block. Recall that there was 32 SVE registers and 16 predicates. This means that we can actually do quite a lot of work in parallel. There's a great, there's a lot of potential for instruction level parallelism because one predicate register is all that's needed for this whole code block. So I can have up to 16 predicate registers doing different things at different times, and reusing them across multiple code blocks or across multiple instructions within the same code block. The last instruction in the loop is an increment instruction for our loop counter. Now recall, I don't know what the vector width is here. I can't, for example, say increment by 32 bits or 32 bytes or whatever it might be. I just don't know. The inc.w instruction says, take this integer and add the number of vector lanes of 32 bits to it. So basically take my vector, divide it by 32, and the result is what I'm going to add to this integer. So this lets me dynamically calculate what the stride should be in this vectorized loop in a single instruction. And it does it very effectively and efficiently. the vector length cannot change dynamically. Once the program is started, the vector length is fixed. So there's not a lot of overhead in doing this sort of stuff dynamically. It's essentially a runtime constant. In the end, we check our predicate against the, we again check our, our loop index, and finally branch if we've calculated the full result. And if we haven't, we continue with the loop. So some key things to notice here. First, the while LT instruction, which is generating our predict P0, which we use throughout the loop body. The incw instruction, which is incrementing our scalar register, our loop index, by the number of float elements that fit in the vector register. And because we're dynamically resizing the vector in the last iteration, so as to handle whatever the remainder might be, there's no drain loop. We can do that through predication. We don't need the additional instructions. This shrinks the size of the binary, and it makes overall for more effective code, and much cleaner and simpler. Now, I showed you the incw instruction that increments x by the number of 32-bit lanes that'll fit in a vector, but there's really some interesting things you can do with this. There's actually quite a number of instructions that will let you stride stride dynamically by different results based on the vector width. Oops. So for instance, you can use this incb instruction. This says increment x0 by 2 times the largest multiple of 3 that will fit within a vector length. It's a very complicated concept, right? This is a very dynamic stride. I could say increment each lane of the vector by the largest power of 2 that's less than the vector length when considered in double precision. This, again, just one instruction lets us do this, but this is the sort of thing that a compiler can generate to vectorize these complex codes. Something a little more simple, but a little more subtle. Increment x0 by the number of active lanes. So before, I was incrementing our loop counter by the number of elements that would fit in the vector. This time I'm incrementing by the number of active lanes in the vector. So this is actually querying the predicate itself to determine how many active lanes and returning that, not the width of the vector register. Increment each vector lane by the number of active lanes. So you can increment not just a scalar, but you could actually have multiple indices which are striding by a number of active lanes. Another challenge for vector length agnostic programming is vector initialization. You'll often see code that says initialize a vector such that all elements of the vector are 0, or all elements are 1, or some constant. If I don't know how wide my vectors are until runtime, then I can't embed that data in the binary and just have it dynamically loaded. So I need different instructions that do this for me dynamically. We can't initialize vectors from a compile time constant, so we use instructions like the index instruction to generate the data dynamically when the program, when that instruction is executed. So for instance, I could say, generate a vector of indices beginning at 1 and striding by 4 for the width of the vector. So this generates 1, 5, 9, 13, 17, and so on until no more of those will fit inside the width of the vector. We could also do things like generate a predicate that is that is as many triples of the true value as will fit in the vector. So in this case, this would be true, 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 and then because there's not enough room for one more triple, we get a double false. Also, loop increment and trip count are not known at compile time, so we have to be able to do things like the incw instruction. You also have the incd. There's different variants of that increment instruction to stride by different data types in the array. So I'm going to take a few minutes and show some SVE.
Let's move before this last example. Let's move to the next question in Menti. While we take a minute or so for people to answer, if there are any other questions in the Q&A.
No questions in the Q&A or in the chat.
Good. So let's see what people are answering. The question is, what's the maximum length of predicate vectors in a 512-bit SVE machine? Okay, so only one question. It looks like people won't answer until I show other people answers. Okay. Okay, so the right answer is, as most of you figured, it's 64 bits. Because the granularity of the data in SVE registers is 8 bits, you only need 1 bit per 8 bits of data. So 512 bits, it's 64 bytes. Therefore, with 64-bit predicate registers, you have enough to control all the lanes in your vector. And with that, if there's still no questions, we'll move to the last example.
Still no question.
The most interesting one. So enjoy that.
Features that help with vectorization. And I'm going to start with a really simple one, a simple horizontal reduction. One of the reasons I want to show this is I'm also going to show a little bit of the intrinsics that you can use to program SVE and give you an example of why you might want to do that. Horizontal operations are fairly easy to understand. We're just taking an operation and applying it across all lanes of the vector. So a sum or bitwise and just taking it and using the values held in each lane of the vector as the operands. So in this case, we just do a sum across all lanes and get the answer 39. So have a look at this example. Here we're taking two arrays, A and B, multiplying them and summing the result of the multiplication into a scalar value. If we compile this using auto-vectorization, a compiler might generate code like we see here. It's SVE code, that's good, so it has vectorized, but we probably could do better, and I'll show you why in a moment. First, let's walk through the code that's been generated. We see that a predicate is calculated using the while LO instruction. So this is to loop over the I loop as long as for all elements for which the I is less than n in the index. We're loading up the A and the B, a vector width of A and a vector width of B in the two agreed instructions using the predicate we calculated from the while LO instruction. And then striding our array index I by the number of double precision elements, basically the number of 64-bit elements that would fit in the vector. Then we multiply A times B, return and store the result in Z1. And then the fadd A instruction takes all elements, every lane of the vector in Z1, and for every lane that's activated by the predicate B0, it it sums them up and stores the result in D0. So every time we loop through this, we travel through this loop body, we are loading a vector of data, summing the vector down to a scalar using the fadd A instruction. So another way we could go about this is by using the ARM C language extensions, basically SVE intrinsics. This is an example of the same code using intrinsics, where now I've specified in the intrinsics exactly where I'm calculating my predicate, which in the C code is called PG. I'm loading two vectors, SVA and SVB, using the SVLD1 instructions. And then I'm summing those vectors into another vector, SVSum. So SVA, SVB, and SVSum are all vector types. SVSum is going to be some number of rolling sums, partial sums during the loop body. We only do our horizontal reduction at the very end in the SVAddV instruction here. The first parameter I've passed to SVAddV, SVP true, is an intrinsic which says do this for all lanes of the vector. So it's activated all active parts of the partial sums SVSum. Essentially, we don't want to miss out on any partial sum. We wouldn't want to use the PG predicate here because in our drain loop, we might have less than the full vector width active if n is not an even multiple of the vector width. So we've gone in and translated the code a little bit. Instead of summing to a scalar on every loop iteration, we're summing within vectors using the FMLA instruction. And then in the final iteration of the loop, right before the function returns, we use the faddv instruction to convert those partial sums using a horizontal reduction down to the final answer in a scalar form. Another more interesting example, I think, is the first faulting register in SVE. This allows us to do some really powerful things. So you've noticed that in all these codes, I have to calculate my predicate, then load my data. Essentially, the load instruction expects a predicate, and the predicate says what parts of memory are valid to read from. But what if you're trying to do something like vectorize strlen, where you don't actually know how long the string is until you read the string and find the 0 byte in the string, which indicates the end of that string's data? You created a reverse situation where, in fact, I have to read the data before I can calculate the predicate. Now, you might think that's no problem, just load as much data as fits in a vector. But what if the edge of your string was against some piece of protected memory that you didn't want to have read? Perhaps it's been marked as protected by the operating system, and reading it will actually cause an instruction, cause an exception to be raised in your code. So it's imperative that we not touch that data until we know precisely how long it is, but we don't know how long it is until we've read it. The answer here is to do speculative vectorization. SVE allows us to use something called the first faulting register, where we attempt to load data from an address, and the result of that attempt is a predicate which tells us how much of the data could be loaded if we tried to load it. So this is how we can vectorize things like strlen that are up against the edge of a protected memory region. So let's take a look at a simple string length example. In this code, this is a simple scalar implementation of string length where I'm just checking every byte in the string, and as long as it's non-zero, I keep incrementing the length of the string. Very straightforward. Now, if we want to vectorize this with SVE, again, we have this problem where we can't know how much of the data is valid until we've loaded it. So for example, if this is our string, and I'm looking for that 0 at the very edge of the string, and I don't want to touch the 2 bytes of data beyond that, that I can use the first faulting register and speculative vectorization to do this. So it looks like this. If we want to vectorize strlen, the first thing we're going to do is set a predicate, which in this case is P0. I use the set FFR instruction to activate our first faulting register and initialize it to all true. And then I do load first fault, so the LDFF1B, where I'm loading bytes of data. And as a parameter, I've said basically load data into the Z0 register using the predicate P0, which we've just initialized to all true. So it's going to try to vectorize, or just trying to load an entire vector worth of data from this address. Then I read the first faulting register, which is going to tell me how much of that load actually would have worked if I'd really tried to do it. The LDFF1B is not really loading the data. It's just saying that this is what I want to do, calculate a predicate to tell me how much of this is actually going to work. Then I can compare each element of the predicate to 0 to figure out how much of that data is actually valid, and then look for the 0 byte in the data that gets loaded. Finally, I increment the loop counter not by the total number of elements which would fit in the vector, but the number of active lanes in the predicate. That is the amount of data which was loaded, which was valid string data. So this allows me to stride forward in an even more dynamic way, where now I'm not even striding by the width of the hardware width of the vector, but actually the amount of vector data that loaded, which was valid. but I just think that's fascinating that you can do that. And then finally, as long as the last thing we touched is non-zero, essentially we haven't hit the zero character, we keep going. All right, I've covered a lot of topics here. Basic introduction to SVE, some examples of SVE features. There's a lot of resources out there that can help you with this, and I find that hands-on experience really is the best teacher. I want to highlight that there are additional hands-on materials, lots of examples that will cover everything from using auto-vectorizing compilers right down into using instruction emulators to explore different SVE instructions. We have some full application examples there. We have some examples which are optimized for the Fujitsu A64FX, so you can see how SVE behaves on that particular architecture and in not just in an abstract way. So this is a good place to go get your hands dirty after this event if you're looking for a little more meat to chew on. This is a pointers to some great references out there, good starting points for learning about more SVE. And in summary, I would say, again, don't panic. There's a lot here. It's a new paradigm, but it's very doable, and it's actually very, it's fun. It actually works really well. When you're programming SVE, do approach it with a vector length agnostic mindset. VLA really does enable portability, scalability, and optimization in your code in a way that fixed width instruction sets struggle to do as well. And as another point, even if you do in fact know the hardware vector width, you might not know what it is at runtime, because that can change what the operating system or the hypervisor decides it should be. SVE was designed for HPC. The first implementation of it is in the #1 fastest supercomputer in the world, according to the top 500. You mostly won't have to write SVE assembly. You mostly can just use auto-vectorizing compilers in your code, especially if you're coming from an HPC background. You're in a good place to get started with SVE. A lot of tools support it, and I do recommend hands-on experience. That's going to be the best teacher for you. A lot of the concepts I've shown here will really start to click once you write your own code. So thanks very much. Have a good time, and best of luck. Bye.
And that's it. I will stop sharing now. And if people have any more questions, Richard and I are here to answer them.
Okay, before I get the question, we will, the presentation is being recorded, and we will put all presentations on the Mont-Blanc website because we have a couple of new joiners. So I know I had the question this morning, but not this afternoon yet. I don't see any questions coming in. So I suggest that we go on to the next presentation that will be more or less a continuation of what was introduced here. Bino, are you ready? Thank you very much, Javier, and we'll see you later anyway.
My pleasure.
Javier is staying with us all afternoon, so you can ask more questions for him. We can handle them offline as well.
Absolutely, please do.
Bino, are you ready to share your screen?
Yes, I will share the screen now. Just a second. Okay, share. So you should see it now?
Yes.
Okay, perfect. So hello, everybody. My name is Bine Brank, and I work in Jülich Supercomputing Center. And here I will give some example of SVE programming. So basically, we will just take what we learned about SVE, what John presented, and apply it to the Saxby example that was already shown. So right away, I would like to invite you all to go to menti.com, where you can use the code and participate in some questions in the end. So maybe I can, or Pascal, you can write the code to the chat.
That's what I'm doing.
Okay, perfect. Okay, so despite not many SVE machines yet available, the SVE environment has already been well developed, as John said. And there are really many resources available for writing and generating SVE code. So here, from the most simplest one, like relying on auto-vectorization, and then all the way down to inline assembly. So in this case, we will take the SAXPY example. So I think you are all familiar with it. Was already presented, and I will first we will check the auto-vectorization, so what the compiler do for different cases, and then I will show how it can be vectorized with intrinsic functions, and then we will take a look at what we can do with these SVE binaries on a machine, on an ARM machine that does not support SVE. So we will take a look at the ARM instruction emulator. Okay, so if I move on. So the first part is the auto-vectorization, as said, supported in all major compilers, and SVE code is automatically auto-vectorized with optimization level 2 or higher. And here is the flag if you are on an ARM machine. So you either first enable SIMD or no SIMD for neon instructions, and then SVE or no SVE for SVE part. Okay, so let's take a look at the SAXPY example. So first we will take a look at our SAXPY example. So this is just a simple file written in C. So here we have in line 12 the SAXPY function, and in line 14 we have a for loop that goes from 0 to n-1. And in each iteration, we simply compute ax plus y. So if we go a bit further down, so this is our main function, very standard. So first we check number of arguments, and the only input argument is the vector size. We read it in, and then we simply allocate memory. We assign random values to the vector, and then we call the SAXPY function. So we take a note of time before and after, and then we print the elapsed time, and then we free the memory. So if we compile this C file, first not enabling SVE and neon. So here I'm using GCC10 compiler, and I am on an ARM machine. So if I compile it, so here without SIMD and without SVE, and here I will use -S to just generate the assembly. And we see this is exactly what John showed earlier. So we have in each loop iteration, so here in L3, we simply load values of x and y. We use fuse, multiply, add, and we store the result back to the memory. So here x3 is the register holding our loop counter, which gets incremented by 1 in every iteration. So this was the basic scalar version. And now let's take a look at the neon version. So here I still have disabled SVE, but now I use the advanced SIMD instructions. So let's take a look at what happens with neon. So here the code is, as you can see, the SAXPY function is much bigger. So here, in case of neon, we have the vector units which are 128 bits wide. So in each iteration, we can compute 4 single precision elements. So this is done in the loop L4. So here we use the neon instructions. So we load 4 values of x and y, again use fuse, multiply, add, and then store the result back. So here you can see that we need to take care of the cases where the n, so the size of the vector, is not a multiple of 4. So that's why we get this big piece of code here afterwards, which basically computes the remaining at most 3 elements in the scalar fashion. So then, but now if we compile it with SVE, so enabling SVE, so here we get the SVE version now using the SVE instructions. And here you can look that we have the Z registers, which are the SVE registers, and the P are the predicate registers in SVE. So here we don't have any loop remainders as in Neon, and we simply use the predicate-driven loop control to simply take care of these cases where size of the vector is not a multiple of our SIMD size. Okay, so this was SVE. This was auto vectorization. So now we can go to intrinsic functions. So intrinsic functions are defined in the document ARM-C language extensions for SVE. And here the goal is to have a set of types and functions to directly access SVE vectors and predicates. And all types and functions have a prefix SV, as you will see. So let's write our SoC example with intrinsics. So here I simply created a new file, and now the first thing I need to do when writing intrinsic functions, I need to include the header file, which I'm doing here. And when intrinsic functions are supported, then also a macro ARM feature SVE is defined. So I can first simply check if this macro is defined, and I do the similar thing in my SoC function. So in case I do not compile for SVE, then this will be ignored, and the compiler will choose the older version of SoC. So here, pretty straightforward, we create a loop counter I and initialize it with 0. Then we create a predicate type called PG with the SV while lower than function. And then similar to what the compiler did, first we use SV load instructions to load elements of X and Y. So here I create two SVE types, dxvec and dyvec. And here I use SV multiply add to simply multiply X, so X SV type and A, and then add it to the Y SV type, dyvec. And then I store the values that are in this SV type temp back to memory with svs store. So then I increment the loop counter and I update my predicate type PG, and in the end I simply check if any of the values in my predicate type are still active. I repeat the loop or not. If not, I'm done. So this was a very quick example of how to use intrinsics. So to compile the file that uses intrinsic functions, we can simply use the same command as we used before for SV. So armv8.2 -a plus SV. And it works, as you can see. Okay, so now let's take a look at what we can do with these SVE binaries on machines that do not support SVE. So here I'm using the ARM instruction emulator. So ARM instruction emulator gives us the option to test our SVE code. So it's a lot easier than Gem5, but it provides no timing information. Still, there are a lot of statistics that we can gather with different instrumentation clients with ARMI, and I will show that now. So first, let's try running our 3 different SoC binaries on the ARM platform and see what happens. And as you can see, the first scalar version runs successfully. The Neon version also runs successfully because this machine supports Neon instructions, and in case of SVE, we get the illegal instruction error. So now if we run it with ARMI, so here I use the 1024-bit version of ARMI, or the 1024-bit version SVE size, and it works. However, the time it needed is much bigger than the scalar and the Neon version, because the SVE instruction need to be emulated, and that is, of course, a lot of extra work. So now we can count the number of instructions executed and instructions emulated with the libins count emulated client. And we can see that 13 million instructions were executed, out of which 25,000 were SVE emulated instructions. So now if I reduce the size of my SVE vectors to 512, we can see that the number of emulated instructions doubles, because with shorter SVE size, I of course need more iterations to compute the whole SAXPY for the whole vectors. Okay, so then what we can do with ARMY is, so in this case, I am counting instructions for my whole program. But in this case, I would be more interested just in the part where I compute the SAXPY. So we can start counting before and after we call the SAXPY function, and we do that with the region of interest. So ARMY enables us to define region of interest, and I do that simply with calling some specific instructions which tell ARMY to start and stop counting. So here I simply define a macro where I inject some specific instructions with inline assembly. So this can all be found in different tutorials and documentations, which I will post later. And now, before and after SAXPY, we simply call these routines. And now, if we compile the file again, and now we can run the ARMY again, but using the options -a -ROI. So this is with the region of interest. And now we can see that the number of instructions executed inside this region of interest were 56,000. And out of this 56,000, 50,000 were emulated instructions, so close to 90%. So if I don't include this -a -ROI, I get back the previous result. So the next step would be to count the number of specific instructions which were emulated. And this can be done with a different instrumentation client. So here, if I use lib op codes emulated, let's see the output. So here I see that the number of instructions executed natively in R64 mode here, and the 11 unique emulated instructions, so SVE instructions, are written to this file, which we can open. And here we see the first column is the number of instructions, and these are the operation codes, which are still decoded. So with ARMY, we get a very handy Python script, which we can use to decode this information. So if we check where our ARMY is installed, here there is a Python script enc2instr. So we can use this Python script to decrypt these operation codes. So the first thing I need to do is the input to this Python script should be just the operation code. So here I simply delete the first two columns. So here I have only the operation codes. And now I can use this Python script. So here I'm just checking if this environmental variable is set that this Python script uses. So here, if I use this Python script with the SVE attributes and with the file I just created, I get the specific instructions which were emulated. So as you can see, this exactly corresponds to what we wrote with intrinsic functions. So we have the store value, the two loading instructions that we use, the fuse, multiply, add, and we have that 6,250 of these instructions were emulated. So why 6,250? So here we use the SAXPY on 100,000 elements, and because we have because we emulated the 512-bit SVE. So in 512-bit, SVE, you can have 16 single precision numbers, and 100,000 divided by 16 is 6,250. Okay, so now a couple of questions for you on Mentimeter. Okay. So if we have the SVE machine with 1024-bit SVE, how many single precision floating point numbers can be stored in these SVE registers?
Can you please show your Mentimeter, Binner?
Oh, it's
not showing. I
it's
mean,
not
we
showing.
can see it on I can see mine on my phone, but
wait,
can you share it?
Your screen sharing is paused. Wait, let me share again.
Yeah. Thank you.
Okay, so we already have some answers.
So, more answers?
More answers?
From the public?
Okay, so the correct answer is 32, because in single precision, each floating point number will occupy 32 bits. So in 1024-bit SVE register, so 1024 divided by 32 is 32. Okay, so if we go to the next one, a bit more challenging. So if we have the same number, of elements for our SoC and the same size of the SVE registers, how would the number of SVE instructions change if DAXP was used instead of SoC? So if we had double precision elements instead of single precision elements, how would the number of SVE instructions change?
Don't be shy, give your answer. It's in Menti, menti.com, and enter the code shown in the chat.
Okay, we have some answers. So what would change if we use double precision numbers? And the correct answer is, surprisingly, the one with the least answers. Because if we have DAXP, then we have 64-bit elements. So if we have 64-bit elements, we can store 2 times less elements in our SVE registers, and we therefore need twice as many loop iterations. So with twice as many loop iterations, we also need twice as many SVE instructions. Okay, so thank you all. I think this concludes my presentation.
Okay, I have a question for you from the audience, a question from Cristobal.
Yeah.
In your experience for irregular and large codes, how well does the auto-vectorization feature work? Can we rely on the result?
So yeah, in my experience, it works pretty well. So if I compare it to, for example, Neon, actually more loops get vectorized because of all the extra feature that SVE brings. I mean, if the code is very complex, then I would still suggest to look at the compiler reports or checking the inline assembly. But in the experience that I had, the SVE definitely brings a lot of new options that compilers can and do use.
Okay. Well, thank you very much. Any other question? No? Well, if you think of more questions later, just enter them in the Q&A tool. So we're running a bit late, so we'll have really a 3-minute break, and then we come back for more for a Gem5 SVE hands-on. Thank you, Binne. Thank you very much for presenting,
you're welcome.
For sharing your experience with us. So Richard and Javier, are you ready to be on again in, well, 2 minutes now?
Richard, are you around? Okay.
Do you want me to stop sharing now so you can share, or?
Yes, that's okay.
Yes?
Yes, please.
Do you want me to stop sharing? Okay, I will do that right away. And you can prepare, you have time to prepare for your presentation.
Can you see that okay now?
Yes.
Good. Okay.
We're recording.
Okay, thanks very much. Hello, everyone, and welcome to the final session of the workshop. My name's Richard, and I'm from ARM Research, and I'm going to be talking about running SVE programs on the Gem5 simulator. So in this session, I'm going to continue the same examples that we used in the previous sessions, and I'm going to show you how to run them in Gem5 Simulator's syscall emulation mode. First, we're going to look at the SaxP example again, and I'll show how that can be built and instrumented for Gem5. After that, we'll have a look at varying some of the parameters of the simulation and see what effect that has on performance. And then finally, we'll have a look at a more realistic HPC example, which is the HiPEAC kernels benchmark. I put quite a lot of detail into these slides because the video is going to be available after the workshop, and I wanted everyone to be able to follow along with the examples on their own. Don't worry if you can't read all the details on every slide. I'll point out all the important parts. So building Gem5 was covered in an earlier session, so this slide is just a quick reminder. And throughout these slides, I'm going to use the Gem5 path environment variable to show where Gem5 was downloaded and built. Also, unlike some of the previous sessions, I'm going to be cross-compiling on an Intel host. So we're going to have to make sure we install the cross-compiler for ARM. I'm going to be running the examples in Ubuntu 20.4 running on Windows Subsystem for Linux. If you're using a different distribution or an older version of Ubuntu, please make sure that you've got the GCC cross-compiler version 8 or above installed, because that was when SVE support was added. So we have a quick reminder of the SaxP source code. SaxP is a BLAS level 1 operation that calculates y equals ax plus y over a large array. And we've implemented that here as a simple scalar for loop. And we've also added a no inline attribute so that we can find the function easily in the disassembly. We've also got a main function that reads the number of elements we want to work on from the command line. There's some code which allocates the X and Y arrays and an A value and assigns them random values. There's our call to SaxP, and we've also got some code to time the operation and print the time to the console. What we'd really like to do would be to generate our performance data just for the call to SaxP, and Gem5 has a set of special opcodes called M5 ops just for that purpose. So M5 ops are some special instructions which are encoded in the unused space of the target ISA, and they're used to control the simulator from within the program being simulated. As was shown in the army example, you could insert these into your program using inline assembly, but Gem5 also provides a library and a command line tool for convenience. You can use the library by including the m5ops.h header file and telling the compiler where to look for them. The M5 tool is a command line tool which can be used in full system simulations from the Linux command line. To build the library in the M5 tool, all you need to do is go to the util/m5 directory of the Gem5 source code and run scons with the build ARC64 out M5 target. And you can build that tool for any of the supported target ISAs, but in this case, we're going to be using ARC64. Gem5 provides a variety of M5 ops. Some of these control the simulator directly, like M5 exit or M5 debug break, or M5 checkpoint. Other ones control how the output statistics are generated, or you can use them to delimit regions of interest in your workload. So for this example, we're going to use the M5 reset stats and M5 dump stats functions, and they're going to let us generate some performance data just for our region of interest. So we go back to the source code. We can add a call to M5 reset stats just before our call to SaxP, and M5 dump stats just after it returns, and that will generate a statistics block just for that call to the function. So again, building an SVE program with auto-vectorization was covered in the previous session. So just as a quick reminder, we just need to compile with the ARM v8a plus SVE flag and the fast optimization flag in GCC, and that will give us an auto-vectorized version of SaxP. And also for Gem5, we'll also want to link statically. It's possible to run dynamically linked programs in syscall emulation mode, but to do that, you need the ARM runtime available, and setting that up can be a bit tricky. So it's much simpler to link statically if you can. And on this slide, if you're following along, we've got a make file, which just compiles the programs with all the flags that we've talked about in the previous slides. So let's see that in action. So first we'll build the M5 ops library by going to util/M5 in the Gem5 source code. And then we can run scons to build the library. That takes a few seconds to build, but when it's finished, we can look in the output directory and find libm5.a, which is the library we're going to link against. Then we can go to the SaxP source directory and we'll edit the saxp.c source file to instrument it for Gem5. So first we'll include the m5ops.h header file, which has all the functions defined in it. And then we'll put a call to M5 reset stats just before the call to SaxP and a call to M5 dump stats just afterwards. And the 0 parameters there are just to tell the simulator to run those functions immediately with no delay. So now we can edit the make file, which I've written most of already. But we'll just add the Gem5 include directory to the compiler's include search path. And we'll say to link statically and add the output directory where we built the library to the linker search path. And then finally link against the M5 library. So now all we need to do is run make, and we can generate our scalar and vectorized versions of SaxP. Okay. So Binna covered this in more detail, but we can also use object dump to look at the generated output of the code. And you can see that the vectorized version on the right and the scalar version on the left are very similar with SVE. And there's almost a one-to-one mapping of instructions, except the SVE version works on vectors full at a time. And that's one of the design goals of SVE, to have very clean auto-vectorization. And in comparison, we can take a look at the generated code auto-vectorized for the neon instruction set. And you can see there's a lot more code that's being generated. But at the core of it, it has a very, very similar vectorized loop. All the other code around it is just to deal with those half full vector kind of drain cases that SVE deals with for you. So to run a SVE program in Gem5, you don't really need to do anything special apart from telling Gem5 what SVE vector length you want to use. We're going to be running in syscall emulation mode using the standard se.py syscall emulation mode configuration script. And to set the vector length in that script, use the param option. And the param option lets you set parameters on objects inside your simulation. In this case, we're going to be setting the SVE, VL, SE parameter on the ISA objects in the CPU objects in the system object. And the value we pass to this parameter is the number of 128-bit units we want in our SVE vectors. So for example, 1 would be 128-bit vectors, 2 would be 256-bit vectors. In this case, we're going to use 4 for 512-bit vectors. The param option uses a special language to describe the objects you want to set the parameters on, and it uses this special syntax that lets you set the same value on a whole collection of parameters. And Gem5 uses a slightly idiosyncratic naming convention here. The ISA here is more like a hardware thread context. So what this line says is that we want to set the SVE, VL, SE parameter on all the hardware thread contexts on all the CPUs in the system. So we can run that directly from the command line, but in this case, let's use a simple run script. So we're going to run Gem5 with se.py configuration. And we're going to run the SVE version of SaxP with 6,000 items in our array. And these lines just set up the system, the memory system, and the caches. And then this is the line that sets the SVE vector length. And that's the main difference to any other Gem5 simulation you might do. So carrying on from where we left off the previous example, we'll just edit the run script and add in the lines for setting the vector length. And then if we run that script, we'll run the simulator, and after a few seconds it will return. And then you can see that Gem5 puts its output in the M5 out directory, and it produces a file called stats.txt, which has got all the simulation output. So by default, Gem5 puts its output in the M5 out directory, but you can choose that on the command line if you want to use a different output directory. And you'll find various simulation output files generated there, but the one we're interested in is stats.txt. And in that file, you'll find one or more blocks of statistics that are delimited with begin simulation statistics and end simulation statistics. And each line in one of those blocks is a statistic name, then a value, then a comment saying what it means. And each file can contain one or more of these blocks. You'll always get one block generated at the end of the simulation by default, and then you'll get another block generated whenever you call one of the M5 ops functions, like M5 dump stats or M5 dump preset stats. Looking in more detail at the contents of that file, a statistics block at the top of it, it will have some system level statistics. And since we're interested in the runtime of our program, you could look at sim seconds, which is the simulated seconds for our region of interest. But that value is quite low resolution. So instead, we'll look at the sim ticks, or the number of simulated cycles of the CPU, which will give us a higher resolution count. And a bit further down the file, we can see some counters for the different operation types. And if you remember that our SaxP loop, each iteration has 2 loads, 1 fuse multiply add, and 1 write back. Some of the instructions we might be interested in are the float multiply accumulate, simd float multiply accumulate, and the memory read and write instructions. So we'll take a look at those later. So to get some more interesting data, let's try running the simulator for a range of different SVE vector lengths. So we'll make a copy of our run script. And then instead of running it for a fixed SVE vector length, we can run the simulator in a for loop across the range of possible SVE vector length values. And because we're running the simulation over and over again, and we don't want to write each iteration's results over the previous iteration's results, we're going to create an output directory based on the vector length. And then we can tell Gem5 to use that output directory with the outdir command line option. So we rerun that. The simulation will take quite a long time, but I've cut the video so we can jump right to the end. And you can see that in our results directory, we've got a separate set of output results for each of the vector lengths we've simulated. And if you're following along with the examples, this is the run script on this slide. So each stats.txt file can have multiple statistics blocks in it. And in this example's case, we're going to have two of those. The first will be for the M5 dump stats for our region of interest that we used. And then the second will be at the end of the simulation, but we can ignore that. And we can extract the statistics of interest that we mentioned before from those files. And you can do that however you like, manually or using some sort of tool. I wrote a quick Python script to do that. And these are the results. So in this table, the first row is for the scalar version of SaxP, and then the other rows are for each of the different SVE vector lengths. We take a look at the instruction counters first. You can see that for the scalar version, we did 6,000 elements in our array. So we've got 12,000 reads, 6,000 multiply accumulates, and 6,000 writebacks, which is exactly what we expected. Looking at the next row, which is for a SVE vector length of 1, which is 128 bits or 4 floating point values, you can see that all the float multiply accumulates were vectorized, the SIMD float multiply accumulates, and the number was reduced by a factor of 4 because we're now doing four operations per vector. And as you go further down that column, you can see that the number of operations reduces accordingly as you increase the vector length. We can also look at the number of cycles taken for the region of interest. And to make it clearer, I've also calculated the number of cycles for the scalar version divided by the number of cycles taken by each row, which gives a normalized speed up compared to the scalar version. And if we graph that, you can see we get a nice linear speed up as the vector length is increased. So those results look almost too good to be true. It's a nice linear speed up. And the reason is, of course, that I chose my example very carefully. So first, we chose a very simple workload, and we used M5 ops to make sure that we only generated data for the region that we were interested in. And we also chose a very, very small working set and a slightly unrealistic memory system as well. So we've got a large L1 cache and quite a long cache line. And we also use the simple memory model, which means we don't have any effects of DRAM timing or banking. So all in all, this means that the simulation wasn't memory bound at all. So we're seeing the SVE speed up for compute alone. So that raises the question, what does Gem5 actually simulate out of the box? And the answer is not any existing CPU. It's a generic CPU model. They've got in order and out of order models, but they don't model any particular existing microarchitecture. And the operation latencies and functional unit configurations are also completely generic. So the moral of the story is that you always need to know what you're simulating. Sometimes the out-of-the-box behavior of Gem5 will be exactly what you want. If you're just trying to get relative performance numbers comparing different microarchitectural features, or you're varying a certain parameter, then Gem5 might be enough for you. But if you need to get absolute performance values, then you're going to have to tune the model yourself. That might be creating your own custom CPU model, or at least you're going to have to tune the operation latencies or the functional unit configurations. So on the Gem5 website, Gem5 is described as a modular platform for computer system architecture research. Sometimes you'll be able to use Gem5 as is, but a lot of the time, to get useful results, you're going to have to configure it or extend it to match your needs. So on this slide, we can just take a quick look at where you can find out those op instruction classes. And if you look in the Gem5 source code at sv.isa or svmem.isa, you'll find a lot of lines that look like this, where the instructions are defined. And if you search for the opcode you're interested in, you'll find the op class defined next to it. And if you take off that op from the end of the name, that's what you're looking for in your stats.txt file. And you can also use the op classes for tuning your model if you need to. That's beyond the scope of this tutorial, but if you do need some examples, you can look at the directory shown there for a place to start. So now we can look at a more realistic HPC example, which is the hardware accelerated.
Sorry to interrupt.
Yes?
There is a question. Do you want it
sure.
now or later?
Oh, yes, that's fine. Yes.
Okay, so it's a question from Timon. Is there a reason why the SVE instructions are reported under the SIMD instructions in Gem5? I'm not sure if you spell it out or say it's just SIMD. Anyway, SMD? SIMD? What do you have? SIMD, okay. I would assume the SIMD instructions are referring to Neon or other fixed size SIMD instructions instead of scalable vector instructions.
Yes. I'm not sure why that choice was made. It could have been that when SVE was implemented, a new set of op classes was created for SV specifically. As you suggest, I think the Neon instructions do use the same op classes. And I don't know why that decision was made, but if you did want them to be differentiated, you could actually change the source code yourself and set up new op classes for it. I hope that answers the question.
Thank you. I don't know, Timon, if is that okay? You can say so in the chat or ask another question. That's all I have for the moment.
Okay, shall I continue?
Yes.
Okay. So HiPEAC is the hardware accelerated cosmology code, which is a gravitational force solver. And it's been designed to scale to a large number of processors using OpenMP, and it can also be SVE vectorized. And we've taken the example from the ARM SVE tools tutorial that was mentioned earlier. So this tutorial was designed to be built on a native ARM SVE enabled host. So since we're cross-compiling, we're going to have to make a few changes to the make file to build it. I'll explain how to do that in the hands-on in a couple of slides, but if you are following the examples yourself, then I've also put the changes you need to make at the bottom of this slide. So after you've made those changes, the compilation is very similar to the SaxP example from before. So the makefile is set up so that you could use a range of different toolchains. So in this case, we're going to tell it to use the GNU toolchain. And we're also going to override the default compilers with the cross compilers. Then when we run the simulation, we're going to run it with the Deriv03 CPU, which is an out of order CPU model that comes with Gem5. And the reason we're using this model, not the minor CPU model from the previous example, is that unfortunately there's a bug in the minor CPU model at the moment, which means that it won't run in SE mode for multi-threaded simulations. We're also going to run a relatively small number of iterations of HiPEAC, because if we ran the default number, it would take a long time to simulate. And to generate some interesting results, we'll try running the simulation for a varying number of CPUs. So in the hands-on section, I've downloaded the code here and I've copied in a run script so that we don't have to type it out. So we'll continue by going to the ARM SVE tools directory and we'll edit the config.make configuration. And we're going to edit the section for the GNU compiler toolchain. And we're going to change the line with the compiler flags. And we're going to tell it to use the generic CPU rather than the native CPU because we're using the cross compiler, and also to link statically. Then we can go to the HiPEAC source directory. And we'll edit the make file. And here we're going to edit the line that compiles the SVE version of HiPEAC. And we're just going to add the compiler flag for SVE auto-vectorization. If we were compiling this on a native SVE-enabled ARM host, then the CPU equals native would handle that automatically. And then we can make the program. Again, we're going to tell it to use the GNU toolchain, and we'll override the compilers with the cross compilers. So this make file is configured to generate a lot of diagnostic output. So when we run it, it's going to give us a lot of information about what it was able to optimize, what it was able to vectorize. These aren't errors, it is working. And then if we look at the output, we can see that we've generated a Neon version and an SVE version of HiPEAC. So at the beginning, I copied in a run script, which is very similar to the one we used before for SaxP, except in this case, we're iterating over a different number of CPUs. And if we run that, again, the simulation takes quite a long time to run, but I've cut the video so we can jump right to the end. And you can see we've got an output directory for every different number of CPUs that we simulated. So like before, I extracted the statistics of interest from those outputs, and I calculated a normalized speed up against the number of CPUs. And as you can see, we get a nice linear speed up as we scale across multiple CPUs. In this case, the results aren't so surprising because HiPEAC's been designed to scale in a multi-processing environment. So these are probably the sort of results you'd expect to see in a real system as well. So finally, I'll say a few words about running SVE programs in full system mode, which is also supported by Gem5. If we run using the standard full system configuration script, fs.py, all we need to do is tell Gem5 what SVE vector length we want to use. And that's, unlike se.py, that's done using a single command line parameter, SVEVL. And again, we pass it the number of 128-bit units we want. And if you remember back to the SVE introduction session, the hypervisor in the OS can also present a lower vector length size to the programs running. So we can tell our Linux in our simulated system that we want to use a different vector size by using the procfs node shown here. So we can echo a value to that. And in Linux, we use that value is shown in the number of bytes, not in the number of 128-bit units. So whatever value you would have passed to Gem5, you have to multiply it by 16 if you want to use it. So in conclusion, Gem5 supports SVE out of the box, and you don't need to do anything special apart from telling it what SVE vector length you want to use. And as always, you need to pay attention to what system you're simulating to make sure that the results will actually be realistic and useful for your purpose. And that's the end of the presentation. So thank you very much for listening. And if anyone has any questions, please feel free to ask.
Thank you, Richard. Any questions? I see Javier has been exchanging with the audience in the chat.
I don't know if as a panelist I can ask questions, but
yes, you can ask a question. You can.
I cannot ask them on the Zoom question.
Oh, you can ask them here.
So I'm just surprised that the SVE extension is working with all Gem5 CPU models. Is that because there is no like special thing for vector extension in Gem5, and this is included in the ISA or in the CPU model directly? Like doing SVE with minor CPU model is a bit confusing for me. This is just this remark that I had.
So it's working. It's working with all CPU models that have the correct functional unit set up. So the minor CPU and the O3 CPU are configured correctly, but some of the other models we've got, like the HiPEAC model, doesn't currently work.
Okay, thank you.
Okay, thank you. Any other question from the audience? You can enter it in the Q&A tool or in the chat. No? Well, if you think of more questions later on, you can visit our website, but you can also visit our virtual booth here at the HiPEAC conference. I'll be on booth duty tomorrow all day, so I can't answer your technical questions, but I can certainly put you in touch with whoever can answer your question. So, well, no, I can't see any other question coming in. So I would like to thank everybody for being here today with us. I would like to thank the audience for attending this tutorial, and my really very warmest thanks to the speakers for preparing this, for sharing their experience of the tools we used in Mont-Blanc. I hope this was useful to all of you. And as I said earlier, all the material we used today will be made available to you. We will put it on the website, but just bear with me. I'll need a couple of days to sort out everything and upload it. So I will send a pointer to the material. So thank you very much, and hope to see you later on the Mont-Blanc booth, and hope to have your visit on the Mont-Blanc website. Thank you.